Hello, everyone, and good morning. I hope you had a restful last night. It's my pleasure and honor to kick-start our tutorial, which is under the title of Recent Advances in Generative Conversational Recommender System. This work has been carried out over a period of a year with a number of our bright PhD and postdocs, Thomas and Amadou, their PhD student currently working at UVN under the supervision of Julia, and Fatima Nazari and Ashmi. Ashmi is a PhD student at TUM, and Fatima Nazari is a postdoc at Polytechnico di Bari. My name is Yashar Deju. I'm currently an associate professor at Polytechnico di Bari, working on a lab directed by Tommaso Di Noia. So it's great honor to have everyone here. So the agenda of today, essentially today we are going to talk to you more about conversational recommender system and their integration with generative models, most notably large language models and other categories. So the agenda of today would be to we'll start by giving some motivation and context to this tutorial. Then we start talking about a little bit, we'll have a systematic approach to provide basically ideas about current system and components which are driving forces behind conversational recommender system, starting giving you some like categorization of this system and what are the core components of conversational agents. Then we'll essentially talk about foundation models, how these systems are integrated with conversational agents. We'll talk a little bit about what is this knowledge foundation behind these models, where is it like attributed to, and we'll talk about simulation of conversational recommender system, which is one area of evaluating these systems essentially towards desired goals. And finally, we'll have discussion focused on evaluation. So we'll have a task division. We'll try to basically divide the speech into our speakers. And so I will be starting introduction. Amadou would be talking more about core system components, foundation models, together with Thomas, knowledge data foundation, simulation, and Ashmi would take care of evaluation section. And finally, we would wrap up the tutorial at open challenges and future direction. I think we will have a break in between, somewhere around knowledge and data foundation. And feel free to take a look at a recent survey that we have written on this work. It's gonna come up hopefully in the next 2 weeks. The title of this work is Advancement in Conversational Recommender System Using Generative Models. So it's a pretty decent survey of last couple of years work on this area, in particular how LLMs, large language models, have shaped basically these advancements. So without further ado, we'll start the introduction with conversational recommender system powered by a generative model. So some motivation actually that we have updated our slides based on a keynote we had here at RecSys is the following scenario. So imagine imagine an information-seeking scenario where a user is looking for, let's say, gifts. We are in Prague for his wife. And what we do in this scenario, we are essentially what we typically do is that we use search engines like Google, YouTube, or similar platforms to run a little bit of exploration of the products that we could buy, their characteristics, and so on and so forth, right? And this is something that typically we do. And finally, when this is done, we use a service like Amazon Product Search, and we buy this item, right? Now, of course, we are here in Prague. We go manually to the shop and buy it. But essentially, this is like this 3 phases of information need, or expression of information need, exploration, and product search is like 3 typical things that we do in an information, in a, let's say, shopping scenario, right? What is the disadvantage of this? Generally speaking, we can say that the customer has to take the burden on herself or himself, and essentially has to go to multiple websites and places to find what she or he wants, right? Now, with with conversational models powered by generative models, essentially one of the core advantages is that we can unify these 2 approaches. So in this scenario, you can think about a shopping assistant like Rufus that is currently actually active by Amazon. And this is essentially a shopping assistant, a conversational shopping assistant that allows you to look up for things that you're interested in, and also to have follow-up question about that product, right? So you can say, this is what I want. It will show you some items in the catalog. It would do some preference elicitation. And the good thing is that maybe unlike search, typical search, the user have the possibility to have follow-up question answers, right? And this is something ideal. No, it can remove a lot of burden on the user on these 2 phases of exploration and search. And the other tools that we have, like those search engines and the platform itself, Amazon Search and so on, these could be seen now as some sort of tools that are being called by these shopping assistant agents. So this is one of the core motivations of using conversational recommender system, essentially the generative approach that can unify these 2. Now, let's start with some definitions of conversational recommender system. So we're going to, in the next slide, we're going to start like from the foundation and gradually go to like more technical details about how these systems work and function. So let's start with the definition of conversational recommender system. What are conversational recommender systems? Essentially, conversational recommender system is an interactive AI engine that can interact with the user, and for their information-seeking task, they can elicit or explicit preferences and finally to provide personalized recommendation. The advantages are obvious. Now everyone knows, thanks to large language models, ChatGPT, they can assist users in a lot of decision-making and information-seeking tasks. They can support product space exploration. And most notably, they can help elicit things that user likes or dislikes through interactive dialogues, right? And one way that we can look at, conversational recommender system and search and recommender systems, like if you look at this spectrum of left to right, you can see search system on the left where you have explicit queries and item or document description, and on the right you have implicit feedbacks of the user. So left is search, right is recommendation, and essentially interactive recommendation where conversational lies is somewhere in between, where things are becoming more merged, and essentially tries to induce user preferences through conversation. I think this is a very nice diagram to illustrate these concepts. What are the characteristics? You're probably, those who are working on conversation, have heard these terms. They're typical terms that you see papers published on conversational recommender system. The terms are like multi-turn mixed initiative, the expression or the interface natural language, and other things. So the first is that multi-turn interaction, obviously. So conversation persists across several rounds, and this we can say stands opposite of a single round or one-shot recommendation. It's mixed initiative. We're going to talk about that. Essentially, it means that both system and users can alternate turns and rounds, as you can see in this fashion scenario. User can use multiple of modalities like voice, text as the primary interface, and through the conversation, the the preference elicitation could be carried out dynamically. Now, from a more high-level categorization, we can look at, we can say that conversational recommender or conversational AI can be broadly categorized into two main areas. Those that are goal-oriented or task-oriented. And the most notable are search and recommender systems. So here we have a task, which is the information seeking itself. We want to, the goal of the system is to surface interesting items so that hopefully the user would consume and reduce the information load to the user. So this is the first area, goal-oriented or task-oriented conversational agents. But these are not the only type of conversational AI agents that we have. There are other categories like chatbots, which belong to non-goal-driven conversational agents that essentially these systems do not have necessarily the goal of information seeking, but for example, to assist user or to serve as a body, as a social agent that can just chit-chat with the user, right? So recommender system, conversational recommender system, or chit-chat agents, let's call them, or chatbots. These are like two very broad categories. So if you search for the term conversational AI, you may see that some papers are not necessarily about recommender system, but still they're called conversational. Of course, for the sake of this conference and our interest, we are more focused on the first category, conversational recommender system. So essentially, everything that throughout this tutorial we'll talk about will focus on some sort of recommendation, which is defined by, we have a catalog of items, we have a user looking for the product, services, and the goal of the conversational system is to match these two through multiple rounds of interactions. Questions so far? Good. This is a beautiful, I think, comparison of several systems around conversational recommender system. Although I have to admit that today, thanks to a large language model, the gap and margins between these systems have been really like narrow. We can see that like a lot of things getting closer and more blurred. But we can go through some of these for the interest of the audience. So on the left, you can see systems that are composed of conversational recommender system. We call them CRS, conversational QA, CQA, conversational search or CS, social chatbots, which we just talked about, and generative conversational recommender system. On the right, you can see commonalities and differences between these systems. Let's take a look at some examples. Conversational recommender system and conversational search. I guess most of us are like familiar with this. Obviously, the commonalities is that both of these systems rank or surface relevant options in multiple turn interactions. Differences: CRS builds a user model, it's personalized. Search focuses on query understanding and retrieval. Conversational recommender system versus conversational QA. Again, commonalities is that both of them dialogue to resolve. So there's a dialogue involved to resolve information needs. In one case, it's recommendation. In the other case, it's question and answering. The difference is that question answering answers factual question, whereas CRS elicits preferences and recommends items. And then we can follow this. The focus of this tutorial is on, let's say, extension of conversational recommender system powered by generative models. We call them Gen CRS. In particular, we are most interested on those powered by foundation models, large language models. But we have to state that large language models are not the only type, are not the sole system, sole generative models that can fuel conversational agent. There are other categories too, but we will be mostly focused on LLM-based agents. Commonalities. Obviously, both of them are the same system, goal-oriented recommendation via dialogue. Now, the most notable difference between a classical or traditional recommender system, conversational recommender system, and Gen CRS is that we can arguably say that, of course, it depends on the model and style. We can arguably say that traditional models have been more rigid. For example, they might have used rules and templates and separate rankers and so on. Generative models are more flexible. For example, they can use LLMs to for freeform NLG, their mixed initiative. And they, as we will talk today, they have, like with the agentic models, they can have tool usage and memory. And all these things will add more capabilities to this system at the expense of some risks that the user may want to be, let's say, accepting, or hopefully these would be mitigated over time. So this is a very nice thing to remember, like if you want to know about like systems and areas surrounding conversational recommender systems. And actually, over the last 2 years, 3 years, and most of the conferences that we go, typically there are tutorials running on conversational agents for the interest of large language models and things that have been like dominating the research and information retrieval as well. Some overview of evolution of conversational recommender system is that essentially we can look at them at things and systems that were before 2017 or 18, which would label them as more like classical models, and in around 2017 and 18 the neural models emerged. And then around 2018 to 21, we have more integration of knowledge graphs and critic-based system in these models. LLMs starting from 2022, 2023, and they introduce other new areas and novelties. And since then, we are now seeing mix of all these previous components. Let's take a look at some previous examples. So if we go way back to 2004, the way like we did conversational recommendation was, for example, exemplified here, where you can see this work by Thompson et al. Building a conversation research, in particular query refinement, but the goal of this system was to elicit user preferences and constraint with regard to item attributes. So essentially what you see on the right, this table, which has some attributes, like you see these food names, cuisine, a price range, Italian, French, so on, and these numbers, these were supposed to serve as a user profile. So this entire thing, which in a smart way was carried out in this research, represented the user profile. And that was the core idea of this research, like how we can elicit user preferences so that we can get these values. So once you have these values, you can provide some form of recommendation. So just want to show you some examples of from where we are going to where, right? And this is a pretty notable work to remember. Let's go a little bit forward to 2009. This work by Mahmoud and Ricci, the title was Reinforcement Learning. And this is using a little bit of a more advanced system. They're using queries about, this work essentially queries users about recommendation attributes during each round, and essentially it learns a policy to choose queries to efficiently yield a desirable recommendation. So this is essentially a work based on reinforcement learning, which tries to automate this process a bit. There's a policy learning mechanism. And again, here, the goal is to understand user preferences about attributes of the items in some, let's say, more intelligent way, right? Like from that static approach, now we are going to more algorithmic driven choice. And this was in 2009, like 5 years later. Let's go a little bit forward, 2016. We have this work by, the name is difficult to pronounce, maybe you know better. But essentially this work by, I call it Chris et al., 2016. And this is a work on iterative recommendation. And essentially, this will collect feedbacks about recommendation item in order to iteratively learn user preferences. So another dynamic work that tries to collect user opinion about items iteratively. And one notable thing about this work is that it explores various query strategies and to elicit user preferences, and you can see this like from the algorithm and the images here. So when was this? This was in 2016. So we are in an area where people are doing elicited, like preference elicitation and so on, right? Now let's go a little bit more forward. 2018, we have this work, Redial, which is now one of the most mostly employed dataset and benchmark for conversational recommendations systems. And essentially, this is also reflected in our survey, which, by the way, you're welcome to take a look. So how does Redial look like? Redial essentially is a work done by Li et al. And the most notable thing about this, as you can see on the right, is that we have a real-looking dialogue. Okay, so it's or they call it free-form dialogue. Okay, and here you have a recommender and a seeker. So seeker is the user, recommender is the system that is providing recommendation. Now, they built around 10K, let's say, of dialogues. And this dialogue was constructed essentially by crowd workers. So it's a dialogue, it's a human-generated dialogue created by crowdsourcers. Conversation between the recommender and the seeker here is like tagged in terms of movies that is mentioned, as well as the preferences that is expressed by the user. For example, it asks if the user has seen the movies mentioned and did they like them, and so on and so forth. So this dataset is focused on movies. And once this is like generated, it trains a dialogue generation model is trained that essentially does the role of a recommender, so it provides recommendation, and then preference here is estimated, and the output is controlled to reference specific movies. So based on the responses that we have, so we go and look at in our database which specific movies is mentioned. So the details are not important. The summary is that this is using crowd working to create free-form dialogues. There's a dialogue generation model. And this is like one of the most notable research currently, like dataset benchmark currently used to drive conversational recommendation research. Actually, Redial has had or has seen a lot of extensions over years, and people have tried to improve some of its shortcomings, despite good ideas that it has brought. So, what are the advantages of this? The advantages of Li et al. Compared to previous approaches, research that I was showing, is that first of all, it looks like a real conversation, right? Because there are humans actually involved here. And actually, it's a real data set. It's a data set composed of multiple turns of interaction between user and system. So essentially, if you have a conversational recommendation model, you can use this dialogue to train this model, simply speaking, right? So it is the first, one of the first, at least we can say, data set that you can train an actual model. But the previous model with those user model, we couldn't do that. Like we didn't have like natural language utterances. And finally, it's an elegant approach for and principled approach for knowing how to train this model and so on. It has limitations as well. Some notable limitations are that conversations aren't really particularly like real, and in the sense that the users aren't actually seeking some items, but they play some sort of game or synthetic game generated by the system in which they are told which item to seek. So it's not like a real scenario where you really, like you have a friend or someone, you talk to him about a movie you want to watch, but it's somehow the type of question that is like exposed to the user comes in the form of this syntactic game in which they're explicitly told which item to look for. So there are biases there, like in the way this starts. And it's not quite clear to what extent the data collection effort could be applied in other settings, right? In particular, those that we do not have a general knowledge. So in the case of movies, users have knowledge about the domain, about the movies, but it's not something that you can really apply to any other domains. And even within the movie domain, it's hard to tell how closely conversation in redial like represent organic conversation. Like, is it really the thing that we do? Overall, with this, what we want to say is that one of the notable shortcomings or requirements in this area is the availability of realistic benchmarks and data sets that can help generation or creation of better and better models. And as you'll see today, there's going to be a lot of details in the following parts about large language models, generative models, where essentially these models are now being used to train better dialogue generation models, and that's essentially have been helping this area of research both on the algorithmic side, like how to better system, but also on the creation of dataset and benchmarks. Actually, we are going to talk about that in more details. In particular, the last thing I want to say, and then our bright PhD students would talk about details here, is the categorization of essentially conversational recommender system that, from a systematic point of view, that we can remember is that we can systematically organize the three main categories of system, conversational recommender system currently in the literature, according to one of these three areas. So I'll try to give a very brief introduction, and the next speaker would talk in more detail about that. The thing that you should remember about all these is that these systems, you can see them as having two main components. Some part of these boxes are focused on the conversational model parts. So in all these systems, you can say that there's a conversational model, and the second part is the recommendation model. So these two models, in some smart way, are interacting with each other. If they're well separated, so if you have a let's say modularized identification of the components within them, they're called modularized. So you can see them in the middle, where you have simple modularized blocks, for example, the initial request, response generation, result generation, so on, user modeling. And this is called like a modularized architecture. Obviously, as you can imagine, the advantage is that it's more transparent, and you can also evaluate each of these subcomponents individually, right? And once they're merged, they become like more what is called end-to-end architecture. And you can imagine that typically these models are driven by some sort of neural models, including generative models. And the last one is, actually we have to change this data flow. We have to call it agentic, but data flow is a fourth one that is not really related to recommendation agents, recommendation system, but the third category would be the agentic ones. And I'm going to talk briefly about them. To summarize, we have three categories of systems or generative conversational recommender system. The first is unified, and essentially these are systems that jointly model conversational recommender system through subtasks. And these are the subtasks that you see. The key word here is the joint modeling of these two. And they typically use a single generative architecture to derive this. As said, the goal is to unify processes through multitask learning and structured, for example, prompting. The modularized one, as the name suggests, things are more clear, more separated, more transparent. This is a conversational recommender system composed of typically several specialized modules. And large language models or language models are mainly used for conversational recommendation or conversation-related tasks, for example, the dialogue management or generating responses. And you can use classical or traditional recommendation models for the recommendation parts, okay? So modularized, unified, and the third category is the agentic ones. And actually we can see agentic one as a little bit advanced version of maybe modularized version, but the reason we are separating is that there are more details there. And by the way, we have another interesting tutorial in the afternoon focused on agentic recommender system, which you are welcome to join. What is the difference between an agentic generative conversational recommender system with a non-agentic? Can someone imagine or respond? So can you think about like a scenario, an information seeking scenario where you would say, okay, agentic ones are like hopefully better or more capable. So what we can say is that if you want to summarize the agentic one, regardless of what modules and systems and so on, the use is that you can see most of recommender system as doing some sort of ranking for us. In the case of agentic system, whether it's conversational or not, we are moving beyond ranking to doing tasks. So ranking is replaced with tasks. In particular, we can call them goal-oriented tasks, okay? Ranking could be seen as one of these tasks, but there could be several other tasks or several other ranking tasks or several other requirements. And that's why this term goal or goal-driven task you'll see in the literature. Let's look at a motivating example, a conversational example that actually currently can be pursued by these systems. And we're going to have a detailed tutorial on this, by the way, in the afternoon, as I mentioned. So imagine this scenario, especially those who have kids. You know, these days it's quite common for the kids to have a theme for their birthday. Imagine a kid wants to plan a Mickey-themed birthday party. Of course, the kid don't care about the money, but we care. And there are requirements here that, for example, there are guests coming, you want them to be gluten-free, and you want to decorate the palettes in the room in certain colors, and there's several requirements of this. Now imagine like 3-4 years ago, we wanted to do this. What would be the right approach? Maybe even today we are doing this, but hopefully this is changing a bit. What was the right approach? We would have like searched each of these approaches, right? So we have several constraints in this case, at least 4. Mickey-themed birthday party, the price, the gluten-free cake, and a red-yellow palette, right? At least we have 4 clear constraints, okay? And it's hard to imagine a single like search that you would put things there and it would do them for you, right? You need to essentially open a lot of tabs, look for cakes, if it's hopefully going to be online, open other places where you can decorate, buy these things, and take care of the gluten-free cake, take care of the price, take care of this. So a lot of, we can say, a lot of opening, closing, and things. And we can say that the notable reason is that essentially search engines are done to rank system like individual tasks for you, not to do a full planning, right? So as we are juggling with multiple tabs filter, the system here is doing the micro decisions for you. The person who is doing macro decision is the user itself, right? And the outcome of this, when the task becomes complex, is friction, missed synergy, suboptimal bundles, and so on. So essentially, the thing is that it can be tiring when there are a couple of constraints, and you may not find things. And you can think about many different examples. So for example, one of the typical examples that typically myself like a struggle always is like finding a good package recommendation for travel. And I don't know if still there are like really good package recommendation agents. You can give things there. It can consider all your requirements for a trip, and it can like recommend you a good travel destination, a good flight, a good routes. And it is something really ideal for us, no? So when the task becomes complex and complicated, this is where these models, like agentic models, shine. And now what happens in agentic system is that we're introducing the complex system for a reason, because the task is also more complex. Essentially what we are doing in agentic models here, you can see the conversational thing, which instead of a single query, you can call it an open-ended goal. So let's not really call it a query, it's more like a goal, right? A task, which is open-ended, which means it has as many requirements as possible, right? And now what happens if you want to summarize what agentic models do for the user is that they try to take care of the macro decision in this case, and let the user express only the information, right? So the way this is done, the two words that we should remember about agents is tools and memory. Now, what is the difference between this system and non-agentic models? The first is that they are defined as systems that are connected to many different tools. One of these tools could be the recommendation or retrieval system itself. So everything is seen as a tool here. And the key term about agentic system is orchestration among these tools. So there is a brain, which is typically an LLM, and we call them language agent, orchestrating tasks among these tools. So like a concept, no? You orchestrate tasks, you decide what to call, when to call, how to call, and so on and so forth. And the way these components and entities work define what is called the workflow. So for example, there could be a workflow that two agents converse with each other to reach a consensus and then produce a recommendation. So it's more like conversing, like conversational. Or there could be things where they are doing peer-to-peer, like ensembling, or you have a manager in the between, and the manager taking care of this. So there's so many different workflows, like we human also decide in a, let's say, in society, no? So back to our example, here you can see a multiple agent pipelines. You can see that there are several tools here. For example, essentially broadly speaking, we can say that the tools are the user context retrieval and the item collection retrieval. And sorry, there is a misalignment here, but it's okay. For example, you can see on the right that for the item collection, we have an agent focused on cake retrieval. So it's looking for places to collect these cakes, and it's also looking for diet consistency, like this gluten-free, and also looking at the theme. Is it like really Mickey Mouse? Now this could be done by one or a couple of agents, but essentially this big box on the top is focused on the cake itself, right? And then lower part, you have the party flavor agent and like the entire theme of the room, for example, no? And again, you have the decoration and so on. So there are a lot of things on the item side, let's say. We are decomposing this task across several agents. These agents themselves could be an LLM, but they could be also a classical recommendation model or any other tool, or even like a tool that you can call with an API, you know, an image recognition system, let's say. It could be anything, right? And on the user side, we could have a similar situation. Overall, with language agent, there is a single large language model that is orchestrating the tasks among them. So this is the first, the most notable thing about this thing. The second thing that is pretty much important for us in recommender system community and information retrieval is the role of memory in agentic models. So memory is pretty much important. You can remember, for example, when ChatGPT was introduced 2 years ago, like when you start a conversation, like on top, over the course of interaction, the quality of chat decreased. Like you started with some broad goal, and you had some minor updates and so on, and you notice that the system is like forgetting your original goal, and it's quite let's say, disappointing or frustrating for the user that the main information seeking need is like forgotten. And now with the new version, which are, by the way, agentic, you can see that the memory has been updated. So the memory here, which you can see here, has several goals. We can see them as long-term and short-term. Essentially, in short-term, it means that when we are doing this conversation, the agent should remember the course of conversation, where you have started and where you're ending, right? And long-term means that it also tries to model your preferences over the course of conversation. And there are other categories which you can also find in the perspective work that we have written called The Future is Agentic, and we have provided a lot of details about that. So this is a third category. So the thing that we can remember for now about multi-agent tools or agentic recommender system are two keywords: agent, tool, and the term orchestration that is handled by a large language model. These are like the three keywords that we can remember about this system. So how we are going to go after this, we will start now from this part on, we will start talking more details about the components of this, the architecture, subcomponents of the example I noted, and I hope that you will enjoy the rest of this tutorial. So thank you very much. I would ask Amadou to come upstairs and follow up.
So yeah, thank you very much for this nice introduction into the broader picture. Now, and also thanks for being here this early. So before the break now, we got quite some content to discuss, and we're going to dive deeper now in these different system architectures that we see in GenCRS. So basically where we start are going a bit deeper into these architectural decisions and show with a few examples how these systems can be built in a unified, in a modular or agentic way. Then we're going to talk about dialogue initiative, the recommendation generation and response generation, which is basically handling the conversation recommendation subtasks. And if we look back to this survey by Dietmar Janach and others, this was basically shortly before the impact of GPT and large language models on the area of conversational recommender systems, but the general architecture and tasks are, of course, still what drive these systems. So typically we would have the central component, which is a dialogue management system, and it basically handles the communication between everything that happens from the user input through internal processes in the system that handle user modeling, that generate the actual recommendations and reason about the current state in the conversation, and then finally the generation of the user-facing output. And of course, with the advancements in natural language understanding and generation, we can take a new perspective at this. So throughout this part, some points that motivate what we're going to present. So after this, I hope it's more clear what these different architectural paradigms are. And we'll also focus on the role that generative models play in these systems. Another thing when we're talking about the initiative in these systems is how are these dialogues handled over multi-turns and how flexible they can be. And last, we'll close with the actual methods to produce the recommendations or responses. And basically, to see a bit of the evolution, this is taken from the literature review we conducted that was mentioned. So this considers papers that were published until the end of 2024. And we can see that GenCRS is quite an emerging topic over the last couple of years. And we can also see that here, highlighted in blue, modular systems are the typical way to go. But we've also seen that agentic systems have gained traction over the years, and the unified systems are often found in early works that explored how large language models could function as a recommender system or a conversational recommender system out of the box. When it comes to environment in which such systems are deployed, most of the works are considering standalone applications, while agentic systems have more work in this domain has more of a applied perspective because the considerations of latency, etc., play a role. So those are often integrated into existing platforms in an e-commerce setting, for example. And this is basically the first system type that was already mentioned, but to give more of a conceptual view to it, what we generally have as the main characteristic is, of course, the unification of all conversational subtasks. So the main characteristic here is that you would have this joint modeling between recommendation and conversation, which comes with benefits, but also with pitfalls, of course. We can either use out-of-the-box foundation models to have a unified system that handle all these tasks, or we can specifically tune them to serve the conversational recommendation task. And what we can see on the output side in a unified system is either the classical CRS task where we would have the conversation history as input and we would output a list of ranked items. But we can also have a more flexible output, which is then really a mixed initiative conversation where the system could handle various subtasks like asking clarifying questions or generating responses that actually contain the recommendation. And in these models, when we talk about the integration of context and how preferences are elicited, basically at a given turn K, the input at least contains the conversational history and the last user utterance, and the context and the preferences as well as the dialogue management is assumed to be modeled by the pre-trained knowledge of the foundation model. And some things when it comes to unified architectures that we can reflect on is, does a monolithic model, or to what extent does it really model and handle all subtasks end to end, or are there multiple steps in between? And an important thing to consider here, because we have this joint modeling, is how well are they able to model the content knowledge and the knowledge they have about our items, and how well can they actually handle collaborative signals, which are critical in the recommendation context. And the question whether, because they jointly model the actual recommendation and the language that's generated around it, can they produce richer justifications within their within their responses. And here we have our first example of a unified system that was early work by Hay and others. And basically they used GPT as a zero-shot recommender, where they used a simple input, the conversational history, a short task description, and a format prompt that defined what the output should look like, which is in this case a list of recommendations. And what they found when we look back at the questions posed, large language models, they mainly rely on their content and context knowledge to produce their recommendations. And as here, recommendation is modeled as a generative task, they noticed that sometimes they would produce out of dataset items, but they also saw that it would rarely produce real hallucinated items that they couldn't match with their with any existing item in the movie domain here. They also noted that the modeling of content knowledge is superior to those of pre-existing CRS methods, while the modeling of the collaborative knowledge is weaker. And this is also partially the case because the output in the distribution of recommender system recommendations exhibits popularity bias when using LLMs as a zero-shot recommender. And as we've already seen here, this is the architecture they used. So we would have the conversation with the last system utterance as a blank that we want to predict in that sense. We would have the task description, so pretend you're a movie recommender system. Then the format prompt, which highlights that a list of item titles should be generated, and then the conversation context, which is fed to the model in this zero-shot scenario, and the output is in natural language a list of item titles, which the authors then mapped to actual movie IDs. And as we already saw, that the foundation models, they lack in their capabilities to model actual recommendation distributions. And part of that is, part of the reason why this exists is that when the response is generated in an autoregressive nature, the ability to really control the recommendations across the whole data set becomes challenging, because we've seen some quite extensive item titles that may be just a list of subtokens. So what they proposed in the subsequent work was to have a two-step adaptation to the conversation task. First, you would condense the sequence of subtokens that represent the item into a single token, and then distill the LLM-generated recommendations as a ranked list in an adaptation phase to align with the distribution of an actual recommendation data set. And the abilities that they highlighted, again, in the movie domain, the pre-trained models, they were quite well familiar with the items, so they could infer a lot of rich information about from complex conversations already. And they also further highlight the limitations with the distribution alignment, especially when the item catalog is dynamic, that we've seen before. So their proposed solution to align a generative model with the chosen data set was these two stages. And on this side, we can basically see a comparison between the item popularity in the actual data versus the item popularity in the generated recommendations. And we can see that before the adaptation, there could be potentially huge discrepancies of items ending up on the other ends of the spectrum. And after the re-indexing to a single token and the adaptation by introducing a bias term, this could be aligned on the outer side. And what they would do is producing item-related conversation, extract the item titles, and then index them as a single token. And in this adaptation step, we see on this side, they propose 2 steps. One is bias term adjustments with multiplicative or additive bias term to actually adjust the output to our underlying distribution, or RecSys gating mechanism, which then goes more into the direction of this modular fashion where you would combine a generative model with a traditional recommender system. And their findings, they align with what we've seen before. However, they also introduced this notion of having a RecSys gating method to improve the modeling of collaborative knowledge. And if we take a look at this, on the top we see these reindex and adapt phase with the different bias terms, which was already able to improve the performance over the out-of-the-box foundation model. And then the additional RecSys gating, where they used FISM and SASREC to improve the outcome of the recommendation. Another work that we see in the unified domain is here, introduced by Yang and Chen. So they basically adapted a foundation model using instruction tuning, and they highlighted the retrieval capabilities of large language models. So they would have this 2-stage retrieval process to first retrieve a set of candidate items based on the existing conversation, and then also retrieve historical conversations by other users that are similar to incorporate some kind of collaborative signal. And they jointly optimized for the retrieval and the generation task, and then on the generation side modeled the tasks of dialogue management as a generative task, as well as the response generation. And they also use prompting to re-rank the candidate items after the retrieval step. So this is more of a multi-step unified approach, but we can see that they jointly model these tasks with a lightweight adaptation. To summarize the main points about unified systems, so about the role of the LLM, of course, or the generative model, of course, is central. It handles most of the subtasks. It models them often implicitly due to its pre-training. We could see that the content and context knowledge about items is very rich and can be used to produce persuasive answers. However, we saw also the poor alignment with interactions out of the box. When it comes to the architectural decisions, we basically have quite a simple pipeline. So we have a single model that handles all subtasks, which can be beneficial in some scenarios. And with this joint modeling, we have a richer or a more natural dialogue flow. However, the shortcomings, they also stem from the autoregressive of generative nature of the generative models we saw, because they limit the control over the distribution of generated recommendations, and they exhibit popularity bias that also results in low diversity in recommendations. And basically this also summarizes the pros and cons that we have with these architectures. One thing that's, I think, also interesting to mention is that with this simplified architecture, it's also harder to isolate error sources that would stem either from the generation, the recommendation task, or the natural language generation task. And in the second type, we already heard about in modular systems. We can do exactly that because we have, like in the traditional systems, these different units and this overarching separation that we see in most of the work in that domain into a recommendation module and a conversation module. So one is more about the content knowledge and the natural language generation capabilities, and one is more about this modeling of the collaborative signal and the user item interactions. And they are characterized by a generative model that is employed to handle at least 2 or more of these modular subtasks. And yeah, therefore, the advancement we have here are that the natural language understanding and generation capabilities are enhanced for the conversation module, while traditional models still handle the recommendation task. So we would see generative models mainly applied in submodules that are not the recommendation engine. And of course, like in all of the system, we would have access to external data about our items or other in some kind of form that we'll also talk about later. And here, considerations to make is how well are these modules separated. So on a higher level, the recommendation conversational module, but also the subtasks. Which tasks actually play to the strength of separating them, and how does this affect this tension between collaborative and content knowledge that we observed. So in the first example here, we can see here in the red box, we can always see in which part of the architecture the generative model was applied. So in the first example, we'll see we have joint architecture where textual context representations of previous conversations are modeled by a sequence model, while a multimodal knowledge graph is utilized to create a user model and to generate recommendations. And then we would have a generative model in the end that solely produces a contextual response template, and then the combination of these two modules is just that the recommended item is inserted into the template. And here the action space is limited because the model could only output a recommendation or and give a response that contains a recommendation. And this is how it looks like. So first, we based on the conversation history, we can extract several types of data. So this multimodal knowledge graph encodes item information. It encodes information about certain entities, and they also incorporate images in a graph manner. And then on the top, we see the modeling of the past conversation with sequence-to-sequence model, which is trained using contrastive learning. So we end up with two kinds of embeddings. The one is the text-based user representation that models the conversation context, and one is the user representation that includes the semantics of the multimodal knowledge graph. And then in the end, we utilize these embeddings to first produce the response template, and then we would simply insert the item in this template. This work here by Kemper and others highlights a more flexible approach to this. So here the LLM is responsible to take care of the user modeling, but also of the dialogue management and the output generation, and how it handles this during a multi-turn scenario is that we have this prompt-based state update where we would have a dictionary that is semi-structured. It features certain characteristics that get inferred after the LLM detects the intent of the user. So we would have some hard constraints which would act as filters on our item catalog, and some soft constraints that might be considered but would not strictly include items, and to model also the flow of the conversation. Rejected items, for example, in previous turns could be represented here. What they also do in their retrieval augmented generation pipeline is retrieving the recommendation based on embedding similarity. And here in this method, they use review data to do so. And with this RAG step in between, they ensure that the recommended items are actually grounded, and we do not end up with out of dataset or hallucinated items. And with incorporating user-generated context and reviews, they also provide a contextualized response. So it looks like this, that we have our current state dictionary. This is translated by an LLM to a natural language utterance, which is then in this embedding space mapped to reviews out of the data set. And based on the query review similarity, we would have our candidate items, but also rich context to provide not only the recommendation in the response, but also an explanation to have a persuasive response here. A further interesting example here is a work that utilizes an LLM for dynamic user modeling. So again, we would have an expert model that produces a set of candidate items that handles the actual recommendation task in the first step. However, we would have some re-ranking step by the LLM to come up with the final recommendations that are shown to the user. And this, in some sense, it can be seen as knowledge augmented generation. And what that means is, in their architecture, they use encoding of two sets or two types of memory. One is user-specific, so we would have historical dialogues by the user if they interacted with the system previously. This is fed to an LLM, which is then used to generate a structured representation actually of the user model, and it can also gradually manipulate it by adding data, merging data, or also deleting data if preferences shift short-term or long-term. And we would also have the general memory, which encodes user conversations by other users. And on the bottom, we see this expert model, which can be collaborative filtering, for example, to generate a candidate set of items, and an LLM that reasons about how these are integrated. And ultimately, with our conversation input, we would, at the current turn, provide the previous utterances, the user model, as well as the collaborative expression and the insights into the reasoning on past conversations, and together with a task description and format requirement in the context, we would generate these knowledge augmented responses. So to sum up what we've heard about modular systems, we have these decoupling of different subtasks, which we already introduced, where the generative model usually handles the tasks that are not directly recommendations. So this is mostly not handled as a generative task. So we would still have traditional methods that cover the weaknesses in modeling collaborative signals. So this is not replaced by a generative model. The strengths of these systems is that we end up with more of an alignment to our target recommendation set, and we can also utilize external modules like knowledge graphs to extract entities and have a richer semantic expression of the existing conversation. And there we can see when it comes to which and how knowledge is integrated, we have these typical models that encode collaborative knowledge and LLMs or generative models that encode content knowledge. And here with this clear separation of these modeling tasks, it makes it easier to optimize them independently from each other. And we can also ground our recommendations with this kind of RAG style architecture. And ultimately, this makes GenCRS more interpretable because we can now isolate the subtasks. It makes it more flexible to generate more multifaceted responses. And on the other side, it also, of course, generates more complexity in our system. So we have this overhead of handling the conversation, handling the different modules, and unifying them to generate a response. And especially, like we saw in this template-based scenario, there can be a semantic gap between the recommendation and the response generation. So we have to make sure that if we have a retrieval-based method, that the context and the language around it are actually matching with the characteristics of the item. And as the last system part, we've heard quite a lot about agentic systems already, and we'll be able to hear more about that in the afternoon in another tutorial as well. But to also summarize this in an architectural overview, we would have these central LLM agents that orchestrate the different subtasks and feature in a closed loop fashion these capabilities of the memory module, the abilities to call tools and the goal planning. And they can also delegate some of these tasks to not necessarily LLM-based expert agents and reason in communication with them to generate the output. What is interesting about these setups is in what way do they actually add something on top of the existing, the previously existing architectures. What additional goals can be served if we employ more long-term planning, and also which challenges arise in actual application of these systems if we add this complexity when it comes to safety or latency if we have more of an autonomous architecture. Just briefly, I think most of the stuff we already know in some sense, but what we envision from this architecture is an enhanced user experience because of the added flexibility, the memory abilities that were highlighted, more contextual precision because of the internal reasoning, and also explainability and transparency about the processes that happen in between. To highlight the characteristics that are central to LLM-based agents even further. We would have in a fully agentic setup this planning and task decomposition, which is most importantly also incorporating long-term goals during conversations. We would have the access to tools that can execute the actions that were defined in the plan. We have the memory and state management that not only is updated during, but also across conversations, and the closed loop fashion in which the interaction and the orchestration gives more autonomy to the system, but still exhibits this goal-driven behavior because of the way how it handles the states and plans. And if we go back to the definition that we can see in the survey paper I mentioned earlier, the strengths of agentic setups really play to the core nature of conversational recommender systems, which in contrast to chit-chat or social chatbot systems really have this recommendation-related goal, which plays to their strength. And as an example that already went a bit into this direction, while it may not fully fit the agentic framework, we would have this work by Feng and others, where we would have different stages of reflecting on the current subtask at the current state in the conversation. And then we would have a selection of expert models that are matched with this subtask, which could be considered as our agents in this sense. And then with the access to various external tools, the task can be executed. And in the end, we have some structured response generation, which is also part of the case why it's not fully agentic, because this takes away some type of the autonomy of the system. And how they do it. First stage, we have the subtask detection, where we feed the central model, which is an LLM as a controller with all of the context and knowledge that we have at the current state. Then this is the output of this is a defined subtask, which can be quite flexible. So this architecture is also extensible because it then can be matched with an expert model, which best fits the deferred task. And then this expert model can access, for example, online APIs or local inference endpoints to then execute the task and provide the output to the response generation module. And in order to have a consistent conversation, this is again structured to provide a response. And the authors here already implemented this closed loop of by introducing reinforcement learning based on feedback. How this looks in a conversation and throughout the course of a conversation, we would have as a first subtask the user preference elicitation, where the model then asks a question about the favorite actors or directors in this movie scenario. Then in the next stage, we would provide recommendations, and as the user asks for it, we infer then explanation as another subtask. And in the last step, we can see rather a search task about item information that is provided or requested by the user. Here we can see a really agentic framework in most of the senses. So we would have two types of general agents. One is a responder agent and one is a planner agent. And we can already see that we have multiple responder agents that serve different tasks, but they all would have the characteristics of a memory module, a profile module, as well as an action module, while the planner agent has in the last step a planning module. And how the flow would work is that in the first step, the planner agent reviews the past dialogue acts to avoid the execution of the same act throughout the dialogue. Then it determines whether we already obtained a sufficient amount of preferences to provide a recommendation. And if the preferences are insufficient, it determines which of the responder agents then jumps in to play to the long-term plan and bring us close or maximize the information gain in the next turn. And after the planner agent produces its output, we can actually generate a system response, so it controls the incoming information flow from multiple agents. And final interesting work in this direction, which is a bit more conceptual and provides interesting ideas for the future. So in this work, the authors, they treat the selections of agents in this orchestration as an actual recommendation task. So what we would recommend is agent items, and those agent items, they exhibit the capabilities of proactiveness, which are important about agentic systems. They have access to knowledge, and they can interact with each other. So we would have environment in which the user can interact with the agent recommender that can interact with agent items, and those can then in the end also interact with the user as well. This is especially interesting because our recommended items, they can evolve over time. They can integrate feedback, and then they can be shaped to serve multiple tasks. But this makes also our scenario quite extensible to also be usable across domains. And we can see that quite nicely in this overview of the 3 layers that we would have on the bottom. We would have our information layer, which grounds our recommendations and information about items and various domains like travel, education, fashion, and those can be accessed by specialized agents, which are the agent items I talked about earlier. And on the top level, we would have this initial interaction by the user and the agent in recommender, which then is able to interact and activate a certain agent item. And this can happen in a 3-stage flow. So in the first stage, we would have the user and the agent recommender, and we would have a selected agent item that then can interact with the user. In this process, there is also a collaboration between the agent recommender and the agent item to make use of the expert knowledge, but also this is creating the feedback loop I mentioned earlier. And the proactive component here really is the orchestrating agent recommender. And in the end, we end up in a scenario where multiple agents can collaborate with each other and their specific knowledge and domains, and then provide the user with really tightly knit information about any request they would have. So, as we've seen with agentic frameworks, they extend the capabilities of GenCRS with their ability to plan long-term with their proactiveness. So they add to motivating the user from their side to interact with the system. They perform multi-step reasoning, and we have a clear task decomposition. And this highlights the way from reactive recommendations to really proactive, goal-driven conversation. Additional user goals that can be solved here or addressed are with the planning, we can see it as a sequential solution that includes the preference elicitation, the actual recommendation that might come with explanation, and then some refinement and further requests for the user that enables like a continuous personalization throughout the dialogue. And also the extensible integration and flexible integration of tools, APIs, and sub-agents. As we already seen or highlighted, those are often applied in real-world application. So this imposes new challenges because we have a further coordination overhead due to the autonomy. We have safety and controllability risks that could cause compliance issues in a real-world application. We also have this trade-off between the latency and cost of this multi-step planning. So we would have to make a consideration whether we have a huge amount of information in a single context versus this decomposition, which means that we need more calls of our LLM, which then might be of a disadvantage for the user if the first token latency increases there. But of course, the interactivity and the proactivity as well as this continuous process are really advantages that these systems can bring. To further advance here on the actual components, what is important in conversational recommender systems and which evolution we see is the different types of system initiatives that dialogue initiatives that have been defined and observed. And what we can see first is that the system initiative is basically not existing anymore because that's what we've seen with button-based interfaces or critiquing in early works. So most of the literature is going to a mixed initiative scenario, while we still have systems that focus on user initiative. And when it comes to the dialogue management, we also observed that most of the works use an LLM as a manager, which means that basically dialogue management is seen as a generative task. And there are multiple ways that we can see later of how this is carried out. To give some examples about these initiatives, here we have a clear example of a mixed initiative scenario because we have this user intent classification and the subsequent selection of actions, which can either react to a user request or pose a request to the user. So we have these dynamics modeled here. However, we also have systems, and I hope it's somewhat readable, but in essence, this is a multi-stage conversation where basically the user poses a request, gets an answer, which is a recommendation. In this case, it's a multimodal output. However, the system doesn't really ask back, so it's request response in that sense. And the other type of user initiative we see are these traditional handlings of the CRS task, where we would have the conversation as an input, and based on conversation, we recommend items. So the only system action is again the recommendation, here in the form of a list of items. And speaking about these recommendations, so we have various ways in which we can actually produce them that go beyond the list we just seen. And first, there are multiple ways how we can present them in a conversational recommender system. And we can see three prominent modes here, which start with the list. Then they can be integrated into a natural language response. And on this side, we can see an example where the output of the system is producing UI elements and multimodal information, so that the user can interact with more than one candidate item. And the paradigms that emerge in case of recommendation are retrieval-based methods, generative methods, and hybrid methods. And hybrid methods we see here as methods that actually use a traditional retrieval-based method. However, the final recommendation task is seen as a generative one because a generative model re-ranks the item. And this is a paradigm that's in some works, we observed this, where the generative model actually re-ranked items, but we can also see, and the slides are available online, so you can take a look at the different paradigms and the literature that exists. But ultimately, we can say that most of the systems are, in some sense, retrieval-based, which goes back to this modeling of collaborative knowledge in this system. And different types to tackle this are, for example, knowledge-aware methods that incorporate some semantic representation of items or the interaction between items, like we've seen in the entity extraction and knowledge graph based approaches. We can also see embedding-based retrieval, like the review-based example we had, or we can have external tools that provide us with a search endpoint. And another thing that we'll see are like controlled generational environments where retrieve items are incorporated into the generated system response. And recommendation response pipelines that use retrieval augmented generation. So in general, we try to really separate here the description of methods that actually produce recommendations or responses. However, it's not always so easy to separate them. Here, as we can see, and as we saw earlier, we have these two sorts of embeddings that are used to generate recommendations, which is more going into the direction of this knowledge-based retrieval or knowledge-aware retrieval. Here we have the example of the embedding-based retrieval using reviews. This highlights the tool calling mentioned earlier. So these are typical retrieval methods that are used before the response generation. When it comes to the generative paradigm, which is more rarely observed, the generation of recommendation is directly happening in an autoregressive manner, which means that the ranking that is ultimately provided is emerging through the order in which the decoder produces the output tokens. And often the recommendations in this sense are generated without having a fixed candidate set. To be able to solve this recommendation task. Often in-context learning is used to infer the context of the conversation, but also to give the instruction of recommendation generation. And in this paradigm, we also saw that lightweight adaptations can boost the performance of generative recommendation. And this is a clear example of this using zero-shot learning. And to conclude the recommendation generation, the hybrid architectures, they basically play to the notion that we have a retrieval step to produce a list of grounded recommendations, which can be item titles or IDs. And by introducing this re-ranking step, we basically imply preference alignment on the fly. This means based on the conversational context, the generative model can incorporate constraints or certain policies to re-rank the item to go beyond retrieval-based methods. And we can also see in this example where they retrieve and re-rank the incorporation of explanations or justifications in this process. And the way this pipeline works is that we have the context and item metadata, which are fed to the LLM. And internally, in this re-ranking step, it produces explanations and a score. The score is then used for the re-ranking, and the explanation can actually be used as a user-facing output to make the decision in that sense more transparent. And this user-facing output is then what we are talking about when it's about response generation. Responses in this system, they often incorporate only a single item, which is different to many recommendation scenarios. They are produced in natural language, and we observe this semantic gap in the responses. And Wang and others, they also noticed that they often observe the drop in accuracy between in modular systems between the recommendation and the conversation module, which can stem from inaccuracies in the item titles that are produced or the information that comes with the responses. What is also a key challenge in the response generation task is this integration of contextualized responses, but it also is, of course, a huge advantage. And we can shortly see a few strategies to integrate items into the responses to obtain contextualized utterances. First of all, we again see the template-based methods with the simple item insertion. We can see some kind of in-context recommendation, which works in this special scenario where they would recommend well-being activities, where the list of possible items, so a whole item space is embedded into the model context. But we can also see examples of controlled integration on the right side. From my side here, we can see architecture that produces the left and right context to a chosen entity or item, so that we have, during training, we model a contextualized response. And on the right, on the other side, we can see this separation between the recommender and the conversation module, where we would have multiple attention heads that decode, that integrate the recommendation during the decoding step. And lastly, to generate recommendations, we can also use RAG scenario, where we would just integrate the item and knowledge we have so that the generative model can infer this contextualized response. So lots of information about the system and its components. Something that I want to add now still before the break is how the generative models or the foundation models can be integrated and which paradigms are utilized to actually adapt them to the task of conversational recommendation. And here we can see the different adaptation paradigms, which start from the more heavy adaptations of full fine-tuning and go down the pipeline to more lightweight adaptations through instruction tuning, for example, and in context learning, which does not come with any parameter or weight updates. So in the setting of full fine-tuning, we have a full adaptation of all model parameters in end-to-end fashion. And this really gives us a tight semantic coupling between recommendation and dialogue. However, it is only feasible to apply this to smaller or domain-specific models. And the advantages here is that we have the strongest form of task alignment, and we can really adapt to a specific target data set or domain. However, this is, of course, expensive when it comes to training costs, but also we need a large amount of data or to adapt it. Also, when fine-tuning end-to-end, we risk of amplifying biases of the datasets that we use, as well as catastrophic forgetting of the general capabilities of the foundation model. And ultimately, we have strong adaptation, which of course hinders generalization. And we can see this kind of adaptation quite well in the control or constraint generation example we've seen earlier, where we would have a optimization on 3 objectives. One is a recommendation trigger that decides whether to recommend or not. The other one is a pruning step, where we narrow the item space by inferring a certain category or type. And then this constraint generator that basically decodes the left and right context upon inference based on an item. When it comes to the second paradigm, which is instruction tuning, we have more efficient weight adaptations. We still have the setting of supervised fine-tuning. However, our input-output pairs are instructions and responses. So the model during adaptation learns how to follow a certain task description formalized in natural language. Compared to foundation models, we have a more stable performance for the exactly defined task. We have, if we define appropriate instruction, stronger generalization capabilities than with full fine-tuning, and the updates to the parameters are more lightweight, using low-rank adaptation, for example. The disadvantages still is that we need curated training data, we need clear instructions in order to be able to generalize it. We are still limited in flexibility due to the adaptation, and still the risk of catastrophic forgetting prevails. And This is an example here. It's from the paper introduced earlier that features this two-stage retrieval step, where we would have instructions for the item candidate retrieval, but also for the conversation retrieval, and then for the other tasks that are handled in a generative fashion, like the re-ranking, the dialogue management, as well as the response generation. And the last paradigm in that sense is the most lightweight solution, which is in-context learning. So we do not have any adaptations on the weights, and we adapt on in inference time. So we have three, I think, well-known scenarios. We would have zero-shot learning, where we would simply give the task description and a given prompt. In the one-shot scenario, we would already give an example of input-output pairs within the context, and few-shot works in the same manner, but provides more examples to adapt. So what we have here is enhanced flexibility because of the low costs for adaptation of the in-context learning examples. However, these solutions are quite sensitive to prompt design and to the examples we provide. So this is quite a challenge still. And in this user study that was conducted in the movie domain, they tried different scenarios of zero-shot, one-shot, and few-shot prompting, where in the zero-shot scenario, together with the rule to generate the response, they would only pass certain genres that are preferred by the users, while in one-shot and few-shot scenarios, they would add some kind of user profile representation of disliked and liked items, and some candidate recommendations as examples. Here we again see the zero-shot scenario, and in the last example we can see different in-context learning paradigms like the direct generation, but also chain of thought reasoning to perform this in a multi-step manner. And the last thing I want to introduce before we can all have a quick break for coffee are the knowledge and data foundation. So in order to produce both recommendations and recommendation, we have all sorts of underlying knowledge that we integrate in different forms. And high-level classification can be seen here. So we can divide the foundation into item-level knowledge, which can come as structured or unstructured data. We see user-level knowledge, which handles the representation of long and short-term preferences, but also with the introduction of generative models adds the possibility to introduce a certain persona or personality, or simulate users that feature these characteristics. And in the end, we also have dialogue corpora and logs that can be utilized, which can either be generic or LLM specific, which we will learn about it a bit more after the break. So here first, when we're talking about item level knowledge, a few considerations is how can the item level knowledge be utilized to improve both recommendation and response quality. How can we balance the general knowledge of pre-trained models with the external data? And which challenges do we have in integrating this into the generative process? And then how can we use the conventional data sets for CRS or extend them to our paradigm? So for the structured knowledge and its incorporation, we have some challenges that have to be addressed. So we need to provide the model with up-to-date information about our item catalog, about the current state of our item, and somehow also make the interaction with these items accessible to generative models. And ultimately, we want to have some grounding and hallucination reduction out of this integration. And the way we can do this is, for example, by introducing knowledge graphs, structured item metadata, or user item matrices in the form of knowledge-aware generation. We can also have certain attributes in a tabular form, or popularity scores as item-level knowledge, or the feedback that has been given by users. And this is often used in modular systems, of course, that employ a traditional recommender module. And yeah, often traditional or widely known recommender systems datasets are used to provide structured item knowledge, like we see in MovieLens, IMDb, or Last.fm. Yeah, here for the item knowledge and also the user item interaction, we can see the graph that models the past interactions between different users and items, which is utilized to model collaborative signals about them. Here we can see past ratings and also the popularity incorporated into context. Another source, yet another source about item level knowledge can be unstructured because of the natural language understanding capabilities we have. So we can use LLMs to derive implicit user preferences from unstructured text, like the reviews that we saw earlier. And this gives us the means to also generate more clues about subjective user experience in our responses, which then results in a more engaging scenario, which we can see here again with the incorporation of reviews as an item profile and an item description. So this is actually a combination then of structured and unstructured data in order to provide a reasoning output. What we can also see in as an emerging paradigm is multimodal item representations. So here we can see different encoder, decoder architectures that encode additional to textual information, visual information. They can encode audio, they can encode video, and this, of course, captures the multifaceted nature of items that we have in many scenarios when we look at the fashion domain, for example. This basically imposes the challenge of how we can fuse these different modalities and how we can play to each of their strengths. On the user side and the user level knowledge, we have challenges of eliciting and handling the short-term and the long-term perspective. So during conversations, we want to be able to detect shifts in topics, but also in the preferences of the users. What is also a challenge is user utterances that contain information about multiple facets or multiple attributes, and how we can decompose them to provide, to elicit the preferences. What is also of course, emerging with agentic systems is memory management, and also adapting to user personas or personalities at the risk of over personalization in some sense here. Further problems can also be that we often have ambiguous or vague expressions, and we want to find ways to disambiguate this to create our user representations. And for long and short term, I think the most important distinction here is between static and dynamic user profiles. And what I mean by that is that in the dynamic sense, we would have we consider the multi-turn nature. So we have updates upon every step and have quite flexible adaptation during conversation, versus static user profiles that use more, that infer the current conversation representation as well as historical information in a single representation. And here we can see an example for this dynamic modeling, where we would have this closed loop of flexible adaptations. This is another example of LLM-generated user profile, which is also dynamic. So we have the capabilities to flexibly add, merge, delete information, and therefore handle this trade-off between long and short-term preferences. And to conclude with a bit of a perspective that we also saw emerging, and these are the concepts of persona and personality. And these can be seen from two sides, basically. But first of all, to distinguish them, persona is more of an external role, so it's rather on the system side who the model is pretending to be. And this affects style, specific role that the system takes, or even the perspective during the conversation. And on the other side, we have personality, which is more about how the model expresses itself. So it's an intrinsic trait that is, on the other side, perceived as more of a stable characteristic over time, which only changes slowly. So, for example, we can have a system that is very agreeable with the user, and express this in the tone, expressiveness, and ultimately the consistency of the conversation. And with that, from the user side, we can utilize this information to alleviate cold start problems, for example, if we consider, for example, alignment with a certain user demographic, which can guide the style or the tone of the conversation. We also can enhance this alignment with the user expectations, because there's often a discrepancy between how user perceives the capability of a conversational system and what it actually can do. And with that, we can bridge this gap to some extent. However, there are many risks, of course, that come with an adaptation to persona and personality, for example, especially when it comes to stereotypes that can be reproduced, and biases that produce harms on the end user side. What we can see after the break is that a persona and personality can also often be used for user simulation, which is quite a benefit we see for future applications. And as some last examples for this persona personality paradigm, here we can see again an application in the domain of recommending mental well-being activities. So basically the assistant, which is called Sunny. It has a persona that is encoded into the context when generating responses. And on the other side, the user can input the current mood, which can then be utilized to adapt to a certain persona. And like we can see here, incorporate traits like the system exhibiting empathetic responses, or be more understanding, or even incorporate certain traits in like emojis or so to fit to the user's mood. What we can also do with personality to have this agentic setup and even more specialized this is encoding some kind of personality into specific agents. As we've seen, these agents can evolve over time. However, with here in this example, they provide them with some traits that are more persistent. And this can be a name that defines the domain in which it's, this agent item is operating. It defines its persona, which here is embody the spirit of a seasoned adventure travel expert. So here it is used to have a more persuasive conversation in the domain. And it also encodes the communication style. And as I noticed that my voice is already getting low, it's quite a good point to end this part of the presentation and have some coffee. And after the break, we will continue with a part on the dialogue, corpora, and logs, as well as simulation that we already heard about. So thank you for your attention so far.
This is the QR codes for the slides, then you can already watch a bit through. We went through different levels of knowledge. Before we talked about item knowledge, now and then we had this several subtopics. We talked about user knowledge, but very important and crucial thing for conversational recommender systems are especially the dialogue, corpora, and logs. We will go a bit into the depths of both of these things, and afterwards we're going to talk about simulation in this context. But this is like some pre-knowledge. We want to just go through that everyone knows what we are talking about. And I mean, of course, everyone knows, but yeah. And the other thing is, now you're wondering what is LLM specific and generic. We will also go through that. But just that you get a little bit of a picture on that, by conducting our survey in the last year, we found that from the papers we've, in the last stage of our selection phase had in our list, 36 of the 49 papers are using conversational datasets. And now you might wonder which kind of conversational datasets. I mean, I think everyone already knows Redial, which was one of the first one in this regard, and then several other datasets came up afterwards. And these datasets we will also show later, that you can just see a bit of the history, how this evolved, and also which datasets of them are based on crowdsourcing or are natural datasets, because natural means just like real conversations without the artificial setup, and which of these datasets are, for example, synthetically generated. Out of these 49 papers, 15 papers were using LLMs to incorporate this conversational data into their models and to output something. This could be like more conversations or some rewriting of conversations and so on. And for the user system log, a very good example for this one is, and I think a lot of researchers are using that quite often, is the Amazon review dataset. Because you have like a user interacting with a system, with a log, because a user writes, let's say, a review to a certain product. And this is in our terminology called user dialogue corpora, in this case a log dataset. Good, but let's go through one example that makes it a bit easier. One of the datasets we also have in the conversational area is the cast datasets. There are multiple iterations. They used cast 19 to 21. These are like 3 datasets released. There is like this track challenge, and they are a very good example what people use as an input to evaluate their system and also to check how well it works in comparison with, let's say, real data or like crowdsourced data. In this regard, in this paper, they worked on different strategies, how to synthesize or work with this data. They had like a rewrite strategy. The rewrite means they rewrote the queries. Rewrite and response was like in one turn they had like rewriting the queries the user asked in different ways, and then in the same turn generating a response based on that. And in the third variant they had a rewrite, then it was stored to some cache, and then a second phase of iteration with the generation in the LLM to create a response. And here they call it hypothetical responses for synthetic conversation snippets. And this is one of the very clear applications where people need to work with conversational datasets. And how they did it, they had like a prompt template for instruction, demonstration, input, where they filled in like these examples from the paper, from the conversational dataset. Another very good example is, and this now goes also a bit into the direction of evaluation, and we will also hear that later from our colleague Ashmi. She will talk about these things more in detail. That especially there you also need to have some kind of data set to compare your methods with. And here, for example, they made use of redial and opendial KG as an input, and their output, for example, was to create synthetic conversational logs for simulation, which is also a very good example how conversational datasets can be used during working on a research project. Another very good example is, and I think this is a very good example to show what we are lacking and why we are going to the direction of simulation. There was a paper by Friedman et al. Posted on arXiv by Google Research in the year 2023, where they essentially built a conversational recommender system around YouTube videos. And what they said is, they highlighted especially the lack of logs or observational dialogue corporas in the field, because back then in time there was not so much out there. And they saw that as a central challenge for their task. And what they did was they generated their own dialogue dataset. They then wrote that they might make it available in the future, but I think it was not. But it is a very interesting conceptual paper how one can approach such a task of simulating conversations and what challenges one has there and so on. This is really a very good example. This is like a snippet from their paper where they wrote. They wanted to do it only through conversation. And I think a very important aspect in the regard of simulation also is that simulation is not just simulating users and recommender system part, for example. Simulation is also simulating the environment around, because it's not always like just two entities. You always have a platform, you have external things influencing the user decision, because the user also do have some other things in their life. And for a full simulation approach, also other aspects should be counted in. And this is a bit what they also wrote here, that they said, they want to have a more compelling approach to such a system. And this kind of also leads us to the term simulation. We will now look a bit into what simulation means in this field and how one can define it, and how it's composed of. But simulation is also what we heard at the conference from a lot of industry experts, a very important thing currently, because what we are mostly lacking is like better input data, more multi-dimensional data, more data in general, or the problem of sparsity of data, privacy concerns, and so on. Therefore, this is a really, let's say, a hot topic currently. Yeah, as you see, we are now already over the half. It's not a simulation part, and afterwards there will be 2 more chapters about evaluation, and then Yasha is also going to talk about the open challenges and future directions. Good, but let's first think about some key questions. First time, like, what is the goal of generative simulation? I mean, we already have some opinion on that we want to make it easier to build conversational recommender systems, maybe to evaluate them. We have different aspects. We're also going to see that afterwards. And also, how can LLMs help here? Because we had some, I mean, simulation is already there from before. There is a lot of research done in other fields, also in computer science, but simulation with generative applications, or with LLMs in this case, enables a lot of more opportunities to us to make this work. And last but not least, and I think this might be quite interesting for all of the people working in this field, is which data sets do we have currently in the field, and how do they evolve over time. Good. But why simulation and why for conversation? As I already said before, if, for example, someone of you wants to build a new conversational recommender system, you might think about, okay, do I find a conversational data set which I can use for evaluation of this domain, which has a certain size for my purpose, and so on. And this was very difficult before, or very labor intensive, or very expensive, because a lot of people used Amazon Mechanical Turk or Prolific or any other platform you now have in your mind for paying people to do something. And with simulation now, it's, I would say, still expensive, because now we shift to hardware-based approaches, and well, but people tend to have at least some GPUs available, and one can run that on a server, and one can simulate these users in a certain way. And what I brought as an example here is one of the papers from Zhu et al., which is about a simulation framework where you can generate conversational data. And they just had this nice picture here where you have like an agent and the other side, like the recommendation part, and they both interact with each other. And as an output, you can have a conversation generated. As I said before, I think this is very important if one starts in this field to think about what problems do we have, and what levels, in which area we need to look into. We already said, okay, data sparsity, availability, privacy, cost are very obvious things. But then also, as we heard before from Amadou, we need to think a lot about user data, for example, how we simulate user data, and also what we do with item data, because we have so much item data. A challenge, I would say, nowadays is also to get better features out of the items we have, because we have more options and tools available to extract things out of items. And last but not least, especially in this regard, dialogue data, because we also want to look how well the system works in a real world scenario. We are now, on this next slide, also going to look into levels of simulation. I think this is just important to see that we started off in the past with empirical data. This is what we had, like, because we can just observe it from the real world. And then there was data sampling, data synthesis, to synthesize some data out of existing data. And where we are heading to, very likely, is the area of full simulation, that one can just simulate the full environment, and you can really see how your system works without the need to really do it in the real world. You can already check it before. And then we might also ask, and how are LLMs now involved here? And LLMs, I mean, this is not just a very short list, but LLMs can help in many dimensions here. They can act as an extractor, a summarizer, they can enrich data, they can act as a meta tool, they can act as an orchestrator for calling the right tools, as we heard today from the agentic talk of Amadou, and many more. But now let's go back and look a bit about what do we need towards full conversation simulation, and where do we start? As we heard before, we have observational data. This is what we all do and did in the past. Which is like classical pre-generative approaches in very easy terms. And if you look at this arrow, you also can see the green one is more authentic and real. This is because we have real data, but we might have less control and bias. Less control and less bias is good, less control is maybe not so good. Of course, there's also bias in observational data, but by simulating things, it adds another level of complexity to topics regarding bias and also control and authenticity of data. Yeah, but how is it composed of? We heard before user, item, and conversation, but in detail, we can also say a conversational data needs to have some task and goal orientation, because as we said before, our study and also our talk today focuses on this regard, because you could also just say, yeah, can have some chit-chat applications, then you would not really have a task or goal, because it's just like talking about not like a product you want to buy or something. And another very important distinction here is also the term multi-turn conversation, because if it's just one answer and one reply, then this is also not really a conversation in this regards that you have a conversational data set afterwards. And last but not least, as we said before, very important is also the item data we need to incorporate into the data sets, that we can really check if, for example, a task or a goal was reached. Yeah, you know it already. A very good example, and we will see it very likely later again, is the redial data set, because it was one of the most prominent ones. And they essentially used Amazon Mechanical Turk to create the data set, where they employed two different roles. They had a seeker, information seeker, and a recommender, but both were played by a human, and they had some specific guidelines, how they should reply to each request and how many recommendations they should make and so on. And this data set is highly used in research, because it's already there since a couple of years, and people are really using that. There are already, like, you will see later, there are many data sets which have the term redial in it. Like, it's a very prominent way how to name your data sets nowadays. Yeah, but now let's go to the second part here, synthetic data, because before we go to simulation, we need to think about how can we synthesize or create data with the help of a generative approach. In this case, we define it as a data generation process, a process that fabricates entire dialogue transcripts so they can statistically resemble human agent conversations, but does not let the synthetic user react to the system in real time. This is the definition we took here. Very important to say here is also that a lot of papers creating these systems or creating synthetic data, they try to check if for example, the distribution of the data they generate is the same as they have in observational data, like comparable data sets, just to see if the system acts in a similar way by simulating or synthetically generating the user data or item data in this case. Yeah, and now I talked a lot about synthetic, synthesized simulation, just also for looking it up later. Data synthesization means we synthesize data from real resources, because you often have a lot of different signals or implicit or explicit signals, and you need to combine them together. You feed them into some generative algorithm and you get something out of it. On the other side, model-generated data means that we create artificial dialogues and interactions with a certain model, which could be LLM-based approach. And user and conversational simulation is just that we simulate users in, as we said before, in a multi-turn conversation, which can then trained and evaluated. Yeah, now, as you heard before, there was redial. Now we also have LLM redial, which was released in 2024, which is kind of similar but not the same to redial. They went for a generative approach here. They said, okay, let's use Amazon review data and let's use that plus a generative application. And we will see it here. They had some data pre-processing going on. They had some template constructions where they said, okay, we have some rules, how we do the recommendations, how the system should simulate the recommendations or like craft together the conversations. And then they had the dialogue generation process, which was done by a generative application. This is like a very recent data set. It's a lot of bigger than redial previously. And yeah, I would say with another one together, these are the most prominent conversational data sets currently. Regarding user simulation, this now brings us to another point because if we want, for example, to evaluate conversational recommender systems, we profit a lot if we can simulate users using these systems because it makes it easier. We do not need to have a user study with people from a certain region with a certain language skill and so on. We could rather just say, okay, let's have some personas defined as Amadou told before. We have some agents, they incorporate this knowledge and then they simulate a user and we can evaluate our method and our approach in a computational way, which is sometimes better, sometimes maybe not. There are other problems also involved because you can run into new biases, but this is like a strongly developing field currently. Yeah, and we also see here a very important term here is that it's a reactive model that reacts to the requests. And it plays the role of a user in a, for example, live conversation and clarification and so on. There are a lot of papers out there where they define different actions the users are able to perform. They either can ask for more information, they can, for example, select a certain product, like they can take a decision as an action, or they can just do some chit-chat or whatever. There are different ways how one can approach that. Yeah, you now might remember the right side of this image here. This is, again, the same paper we showed before, but now with the left part where we see what they did. Because this was a very interesting example to show that you can add some real data sets. You then have a plugin manager where we can I mean, they called it plugin manager, but it was, I think the original paper was from 2024. Today you would say you have some model context protocol with some tool calling and so on. But what we also observed during working on a study is that people did some things, named it in their own way, but later there was like a one unified name for this pattern, which is, for example, the model context protocol or tool calling. But tool calling was also sometimes done before, but people just did not call it tool calling, which makes it quite interesting to see here. That this idea is sometimes already there before, but then later there is like a common agreement in the field that we now have one name for this certain programming paradigm. Yeah, and what they did here was that they had, as I said before, different actions one can take. They had a memory. Memory is also, as we heard from Amadou, a very important aspect of a conversational recommender system or of a simulator because we need to somehow keep persistence, long and short term, and have some like profile with preferences and actions you can do. Yeah. Now let's think about full conversational simulation because I think this is the most interesting thing, but I think we are not yet there to really fully simulate a conversation with user, agent, and all the environment. But there are some papers which are going to this direction. We define it as a closed loop environment where we essentially get some reward mechanism back to the system that it can improve itself, and that we model especially the users and the external world with this simulation. This is, I think, quite interesting, and the papers are going to that direction. Like we will very likely see in the future some people publishing more work in this regard. A very good example here is from Huang from this year, 25, in transactions of information systems, where they essentially proposed a system where you already cover a lot of these aspects. You have like this overall area, you can now see in the red rectangle, where you have some states it went through, and also the reward cycle back. This is, I think, the most important thing here. You have some kind of brain which interacts, and you have a learning concept which helps the system to improve and to change its behavior. As we also saw before, here we have, again, long and short-term memory. We have tools. Here we already are in the world of tool calling. With different options one can choose. One cannot see it. With an execution plan and with different tasks one can perform, like query, retrieval, ranking, and so on. And some, I think this is also a very important aspect here, that you have some planning aspect that the system can think what action to take next. And this all then put together into a user simulation with some agents and so on. This is like one of the most recent papers you can have currently in this area. But of course, later in the Q&A, we can just discuss. Maybe there is already something new. As I saw yesterday, there was also a new conversational dataset published at RecSys in a poster presentation, but I will show you the title of the paper later. Let's now talk about classic and generative datasets. This is what we already currently have out there. This is also a composed list of what we found in our survey we did on the left side. On your left side, you can see how this evolved, also split into classical and more generative approaches, because we had redial first, then we went to OpenDial, GoRecDial, Inspired, then another Inspired, DoRecDial, then a 2.0, UNIT. All these datasets except for UNIT are crowdsourced. Crowdsourced means the people creating the dataset paid some people to interact in an artificial scenario to just generate the conversations, except for UNIT. UNIT was it's out of the e-commerce domain, where they just use the real conversational data, where they just use real conversations from a real system. TG Redial is quite interesting here in this regard, because it was from 2020, but they already used some templating and guided mechanisms to semi-automatically generate the data, which makes it quite special in this regard here, because all the other papers here are from later, like they're all from the generative area. You can see that there was this Friedman et al. They did their own synthetically self-generated data set, which was the Google research group with YouTube. And then we started off with LLM Redial, with Perl. Then we had some other papers where they sometimes did not publish the data. As I said before, they especially highlighted that there is not so much out there for this purpose. This was in 2023. For these data sets, we do not have public availability, which is in some, especially I think for the Young et al., it had some, it was a medicine-related topic where they already said they cannot make the public. This is how it is sometimes. Very nice is that yesterday from Martina et al. Was another new conversational dataset published, which is available online, which is from the colleagues in Italy from the SWAP group. We just saw that today because the poster presentation was yesterday, and then we said, okay, let's include it into our presentation here. Just that you won't see the TG redial because it's quite special. We thought we just also bring it up here. They have these topic threads which kind of guided the system through generating the conversations, which made it to a very nice example for how one can create such a data set in a more semi-automatic way. And then they had in the end some user bot interactions here, which was really nice to find. On the other hand, as you already before saw, for LLM redial, it's more like the classical generative approach where you start off with some input data, you do some pre-processing, you define your templates, your actions, and then you run the generation of the different conversations. Another very good example here is also Pearl, which is also from Kim et al., which was published last year, which is another good example for conversational data set, where they used also a similar setup with user review DB from the user side, and they have some preferences, target preferences, and also the recommender phase, and then it generated the dialogue based on a given data with generative approaches. To give you another picture or a view about how Gen AI changes the field, like just imagine 2018 we had redial, which was like the way to go with 10K dialogues, 182.1K utterances in a single domain. And then a couple of years later, we now have like LLM redial with a generative approach. They use GPT 3.5. They had turn goal templates, as we saw before. They used this Amazon review dataset, plus the user histories. And then they ended up with way more dialogues and then utterances over 4 different domains because they were able to generate this in a very efficient way. And also, I assume with less cost, if one looks through the papers, it seems that they did not pay as much as the redial here. Which shows that this direction is quite interesting to investigate. They also, in their LLM redial paper, brought an example, like a comparison between, on the left side, you see LLM redial, on the right side, you see the classical redial dataset, just if you are interested in how such a dataset looks. Which is really good because they had some like historical interactions, user ID, and some like preferences, and then this is with what they generated the conversational data set. The next thing, and this is the last slide before I move over to Ashmi's presentation about evaluation, is just a list of all the classic to generative data sets. Just in case you are interested in one of them, you can just open this slide and take out whatever you want. This is like a list of every conversational data set we showed today to you. Good. This concludes my part. I had half an hour time. I think I got it quite good. And now I would like to hand over to my colleague Ashmi to talk about evaluation in this field. Thank you.
Thank you so much, Thomas, for the lovely presentation. My name is Ashmi, and I am going to talk about the evaluation of conversational recommender systems. And so let's get started. So we have segregated the evaluation along several dimensions or key dimensions. So the idea is that we differentiate or categorize the evaluation, like what is being evaluated using the different types, the output types, so the different outputs that you have, which could be either user-facing or the non-user-facing. So don't worry about it. I will explain each of these terms or the buzzwords in a minute. We will have like detailed explanation for each of them. I'll just give you an overview for now. And then after we have evaluated what, the next part is that on which basis do we conduct these evaluations. And this kind of refers to the quality aspects of thing. So, you know, like how good the quality of recommendation is, or how good the dialogue efficiency is. So like how many turns it took for the dialogues to converge, and so on. Once we have that, the next part is like how or what are the different paradigms using which the evaluation can be conducted, which could be offline or online or user studies. I'm sure most of you are aware of these metrics. You probably may be a bit confused by the grouping, but once we go in the details, I'm sure like all of you have encountered them at some point. And then the next part comes is like, okay, we have done these different types of evaluation. Now, who is doing these evaluations? So whether it is using some sort of automatic metrics, or we are employing humans to do it, or it's even like an LLM as a judge. And last but not the least, for whom are these evaluations being conducted? So whether it is for the different stakeholders. So as you know that recommendation system is always a multi-stakeholder problem. So you cannot or you should not design recommendations that are catering to a single stakeholder, and it should always make sure that it's kind of considering the interests of all the stakeholders. So in such a case, which stakeholders are being considered for the recommendations? So we have like the consumers, item providers, and others, so like society or even the platforms and so on. So let's get into the details of each of these questions or the aspects that we identified. So as I mentioned, the output type, like what is being evaluated, and for that we have the user-facing and the non-user-facing. The user-facing is what the name suggests, what exactly the user sees. So basically like any kind of natural language terms or the recommended items or the explanations that are being generated as a part of the whole system, or even like if it's a multimodal system, then the images or videos or whatever is being shown to the user. So it's quite straightforward. And the next part is the non-user facing. So most of the work, while the focus of conversational recommendations are like user-facing aspects, but there are also aspects when they focus on the non-user-facing things, so which are used to build the system. So for example, like the embeddings, or if there's some sort of like augmentation, data augmentation happening, or like retrieval happening, so and how good that retrieval quality was, or the augmentation was, and so on. It could be also like some sort of hidden reasoning paths, which are not really like the user is aware, or maybe the user is aware but user doesn't see it, and could also be like internal state updates and so on. Right. However, like if we analyze the trends, we realize that the current research is kind of focusing mostly on the user-facing side of things. To be honest, for a conversational recommender system point of view, it's kind of obvious, or it's kind of makes sense that they do, or most research focuses on that, because the idea is that we want the user to accept things. And the non-user facing outputs, what we, from the papers that we analyzed, the only way they were kind of being evaluated were ablation studies, where they were kind of like, okay, we have this really nice embeddings done, so we would like to see what is the impact of these embeddings, or what is the impact of this component on the entire system. So it is more like evaluating how good this specific or their novel component is with respect to the whole system, but not like specifically targeted to the actual evaluation of the component. Right. Some studies also extend this with some sort of sensitivity analysis, but it's not that prominent, I would say, in literature, or at least the literature that we surveyed. So as I mentioned, that this is kind of obvious that most work focus on the evaluating the user-facing side of things, because the idea of Gen CRS is to make sure that the user has a good experience, because it's mostly like the user should be satisfied with their what is being presented and their conversations that they have with the system. And as we say that the evaluating the journey, however, is also kind of important, because obviously the user might have a very smooth experience with the whole system, but then maybe something is buggy on the way. And then, so it's also important that the journey is evaluated. So we should make sure that the dialogue coherence or the interaction efficiency, like how well the user is interacting with the whole system, that there are not so much lags or the latency is not too much. And all these things should be made sure that they are also evaluated individually and properly for a whole comprehensive system that functions properly. Right. So this brings us to the next part, which is the quality of evaluation. Or so once we know like what is being evaluated, the next idea is that how well it is being evaluated, or on what basis are they being evaluated, for which we have identified like 6 different areas. So the first one is like the task effectiveness. And so for each of these areas, we have also identified certain questions that you can ask. So for task effectiveness, it would be like, did the user actually find what they were looking for, or they were not satisfied with that? So basically it is evaluating the recommendation quality of the final recommended item. Then the next part is, since it's a conversational setting, like the dialogue or task efficiency. So how quickly did they find it? How many turns did they need to converge? Because obviously something, if they need more turns, it's worse than something if you converge in a conversation to like in a fewer turns. Like the next part is obviously the conversational quality. How good was it? The conversation, whether it was natural or coherent, or was it just like hallucination and chit chat, and what was exactly, I mean, chit chat is not bad, essentially, depends on the context. The next part is the subtask performance. So in addition to the main task or the main goal of evaluating the conversation, was the system good in also handling the secondary tasks, like how well did the internal modules work? Were they okay? Were they all converging towards the same goal? So that is kind of the subtask performance. And then we obviously have like the trust and the user satisfaction. So how much the user is satisfied with the system, or how much does the user actually trust the system? So if you do not trust the system, there's no way the user is going to be happy with the system and will be, free to use the system. And last but not the least, we have the ethical considerations. So is the system actually ethical? Is the system, does it have biases? Does it have, privacy concerns, and so on? Among the papers that we surveyed, we saw that there were like most of them, you can see that around 80% of the papers were focused on evaluating the quality of the recommendations or the task efficiency. And some of them did evaluate the conversational quality, but like the rest were not really focusing a lot on these, the other aspects that we discussed. Right. So let's go into the details of task effectiveness. I'll quickly go through these. So the idea is that as I mentioned, it's like ultimately how good the recommendation quality is. So did the user manage to find what they were looking for? And for this, the common metrics, we will discuss the metrics again a bit later, but just to give you an overview. So the metrics are like the hit rate or the recall, NDCG, and so on. Whereas if you are doing it on an online evaluation, you always try to do the user acceptance rate or the click-through rate, and so on, because you're kind of doing an A/B testing, or you have like an fully functional or production-ready system. And so this is basically it. And these are some of the papers. The references are in the paper and as well as all on our website. So you see, like, these are some of the papers that use these metrics. The next, as I mentioned, is the dialogue or task efficiency. So how many turns turns or rounds that it takes to the user to actually arrive at their recommended item that they accepted, for which we also use like the number of dialogue turns, could be the turns to success, could be a measure of that. The time to actually complete the task, or even like the system latencies, could be important metrics for these things. And as I mentioned, there are not too many papers covering this. For conversational quality, which is essentially like how good the conversation was, how coherent or how natural it was. For that, we do have some fluency metrics like perplexity, or some content overlapping metric like how good that was for Blue on Rouge. Sorry, my French pronunciation is very bad. Or you can also have like accuracy, like recall and recall for this. These are like some of the objective metrics. So for this, you do not need to have, you can just run it offline. But then for some sort of subjective metrics, we will discuss this again when we discuss the metrics, but I'll just quickly give you an overview. Subjective metrics, like when you're using like humans in the loop to evaluate like how good the quality was, like naturalness or how persuasive this was, and coherence. For subtext performance, as I said, like there are very few papers that actually evaluate that, although we think that this could be a very important dimension of evaluation. So we have like intent recognition, which can be measured using accuracy, or like slot filling, which can be done by precision, or entity extraction using F1 score. For trust and user satisfaction, we basically use a lot of the subjective metrics to understand how satisfied the user was. But surprisingly, like for exact user satisfaction, we did not have that many papers in our survey that explicitly asked the user, like, how satisfied were you with our system? So yeah, mostly they were asking about like how, what do you think about the perceived relevance of the items, or something a little bit indirect compared to the exact satisfaction. For ethics and biases, unfortunately, we realized that there's a significant gap in the current literature, which kind of does not address this. So most of the papers are kind of focusing on more like evaluating the recommendation quality, but then not so much on whether or how harmful their recommendations are, or how like ethically abiding these recommendations are. So now we come to the next part, which is the how part. So how are these evaluations done? So basically, whether they are offline or online or user studies. So by offline is like you already have your data, you have your models, you evaluate them offline. Online is basic, and this is something that we observe in like 80% of the papers. Online, we have it like when you deploy it in a production-ready live environment, and then you gather user interactions from that system. And which is the least, because this is also the most expensive way of putting things. And you like usually these are like companies or big companies doing this. For like small scale researchers, it's typically not the case. And user studies and lab experiments, these are often seen in addition to offline experiments to prove that the results of the offline experiments are in line with the user studies or the findings of the real user. So that is something that we also see in a very high number of papers. Yeah. So offline experiments are, as I mentioned, they are pretty easy and low cost because you can just do it yourself. You have like less reliance on external sources. So for that, we have like two main approaches. So one would be the automated metrics that we can use. So like the standard metrics like recall, precision, NDCG, and so on, depending on your use case and what you are trying to do. Or the other one would be the user simulation that Thomas just mentioned before. So you just simulate a bunch of users, and then you try to like evaluate how, from the user perspective, like how well your system performs. And let's see a quick example of this user simulation. So this iEval-M, which was a very interesting work that we found. And this is basically what they are doing is that they propose a new interactive evaluation framework using ChatGPT, and for like two distinct use cases, one for chit chat and one for like a specific conversation. And they show that when you actually give ChatGPT some sort of like prior information or like the user simulation, then it does better than without this information. Right. The next part is the online evaluation, which is the technically like the gold standard for assessing how well your recommendations are performing or your system is performing. So as I mentioned, that this is also one of the most expensive ways of doing it, because you have a live system and then you get the user interactions from the system. It's also an uncontrolled experiment. But in our research only, or in our survey, we only had like very few papers which were actually using the system to evaluate their results. So for example, this event chat that we use or that we found was evaluated online. So it is, they developed an application for this startups in the leisure or the events domain, and then they put it live and they did an A/B testing. So A/B testing is a very common way to assess this, where you have like, for example, 50% of the users see a certain part of your application and then you are evaluating them, versus another 50% sees like a certain other part and then you see how the users behave, and then finally you have some insights into the performance of these two features that you had implemented in your application. Right. The last part is user studies and lab experiments. I think I will not go into too much detail, but because a quick show of hands, like how many of you know like what user studies are? So I guess, yeah, quick show of hands, yeah. So it seems like a lot of people know, so I will not go into too much detail about that. So they are mostly, as I mentioned before, they are mostly used in addition to offline experiments to make sure that all the results are kind of aligned. So now coming to like who is doing the evaluation. So we have the automated metrics, which are the algorithmic approaches, or mostly the offline metrics that we are using, where we do not have any external dependence. And as you probably would have guessed from the previous statistics, we also have the maximum number of papers which employed these automated evaluators. But then also a significant number of papers had the human annotators involved in making the decisions or like evaluating the recommendations. And then now with the LLM, the emergence of the LLMs, there's an increasing number of papers which are using LLMs as an evaluator. So where they actually use like stronger LLMs like GPT-4 or Claude 3.5 or even 4 or something similar of that that size to evaluate like responses generated by other smaller, possibly smaller LLMs. Right. So as I mentioned, the automated metrics, they are very consistent and scalable, because obviously you can just take a static data set, you can run your metrics and then you are done. But then it's like very good for offline evaluation because it's also cheap. However, the problems it comes with is that it often fails to capture some nuances that you may have or some outliers that you may have in your data, and then, or if you have some like something to do with like the coherence or the conversational quality or the user satisfaction, these nuances, the subtle things are often, they fail to understand this, right? So for this, we are usually evaluating the ranking or the recommendation quality, or sometimes also like the NLG stuff using Rouge or Blue. And regression prediction error, so the standard error metrics like MAP, MAE, so on, and classification and prediction accuracy, so precision, recalls, etc. So we actually categorize the automatic metrics into like ranking, NLG, and classification, as I mentioned before, and then we see like how many papers we have, and we see like most of them have a very high recall, like not a very high recall, but then most of the papers are computing recall. And then followed by the others. So we also have like, say, perplexity for fluency and so on. So, yeah. The next part, the human annotators when they are used. So this is a rather expensive way of doing it. It could be an online study or even a lab experiment where the humans are being used to annotate your data or rate the quality of your recommendations or your results. It's a very time-consuming as well, and obviously very expensive, but they often help to understand or understand the nuances, or even help to, even if you do it on a subset of your data, you can get an idea of how good or whether the results are aligned with the LLM responses or not. Right, or LLM or offline metrics or not. So the commonly used subjective metrics that we found in our papers are these. So I'm not sure if it's super visible, but the S1, S2, S3, and so on are like written on the side. You see like fluency, coherence, informativeness, and so on. As you see, I mean, these are more or less like easy to understand and self-explanatory in their own. So yeah, and we see that most papers actually evaluate for informativeness and helpfulness, followed by fluency and grammar, but then the others are not so much evaluated from like the papers that we surveyed. We also see a significant gap for the beyond accuracy metrics actually. So like novelty, serendipity, and so on. So for LLM-as-a-judge, it is a very popular, it's gaining a lot of popularity, where we are using LLMs to evaluate the quality, as I mentioned, of responses, because this is a very scalable thing. So you can use like huge amounts of data to be evaluated by the LLMs or the stronger LLMs. And a lot of papers are doing it. I mean, I think it's gonna also increase in the future, like the number of papers that we will have in this domain. So let's quickly look at one quick example. So there's this RecSys paper where they basically use LLM reasoning to enhance the personalization. So they use LLM-as-a-judge to verify or improve the responses of that were actually generated by an LLM. So it's kind of like a recursive process. And this paper, it's also linked. So if you want, you can have a look at it. For the sake of time, I will try to hurry up a little bit. So the last part is the stakeholders. For whom are we doing the evaluation? So whether it's the consumers, item providers, or others, as you know, like this is a typical recommendation scenario where different stakeholders are there, and then each of the stakeholders have their own goals of matching preferences or maximizing. So like the user's goal is to maximize the preferences, whereas the item provider wants to also get like maximum exposure, whereas the platform or booking platform, in this case of like hotel recommendation, their goal is to maximize the commission and so on. So everyone is kind of striving to maximize their own goals. And in that case, ideally, a recommender system should prioritize the needs of all these stakeholders and create or generate balanced recommendations. However, in reality, we see that 93% of the works actually focus just on the needs of consumers, and very, very, very few works actually focus on the needs of the other stakeholders. So, yeah. So other stakeholders, among other stakeholders, we found like maybe 2 studies which were somewhat looking into, not directly addressing item providers, but like somewhat looking into this direction. So there was this paper by Wang et al., mitigating popularity bias to enhance fairness. However, like it was, as I mentioned, it was pretty indirect about it. Whereas there was this other paper by Kim et al. In 2024, which was about tackling user item rating bias for a fairer assessment of items. The other part is, or the others part of the stakeholders are basically the most often overlooked by most papers are environment or society. So the environmental impact of these models or these systems are often neglected and undocumented in literature. So how much environmental impact or the CO2 emissions or, that's not a lot of information is available for that. However, some works are now trying to focus on like including society or environment as a stakeholder, and then trying to generate sustainable data recommendations. So they are either focusing on the system design part, we will see an example soon, or the data generation, which is also synthetic data generation focusing on sustainable metrics. Yeah, so let's have a quick look at the thing. So this is actually our work, CollabRec. It's a bit of shameless plug, but yeah. So this is our work where we use like multiple agents. Sorry, it's the text is a bit yeah. So it's using multiple agents to come to a decision where they are moderated by a non-LLM moderator, and then they take like multiple turns to negotiate and come to a decision where finally the final recommendations are all sustainable. So there are like 3 different agents: so popularity agent, sustainability agent, and sorry, what was the sustainability agent and the personalization agent. Yeah. Right. So the other gap I mentioned is the data generation, is also because the problem is that we would love to do this work, but then we would love to generate sustainable recommendations, but the main problem is that we do not have any data sets that are relevant for this. So for that we need like data sets, and this is again a small shameless plug. This is our work that we published this year in SIGIR, where we actually generate a bunch of natural language queries, synthetically obviously, and that includes sustainability information, and then in regards or as an answer to that, you have a sample of cities, European cities that are being recommended or can be used, so you can use them for that. And we also present a knowledge base of a bunch of European cities, 200 European cities. So for example, if you have a persona or a persona, which is like wanderlust filled trader, blah, 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 and then you have a very specific query which is being generated by the LLM itself, which kind of takes into consideration your constraints and the persona, and yeah, that can be later used for generating recommendation. So yeah, like quickly going over the challenges that we have. So the main problem, as I mentioned, is that for the RecSys is the traditional evaluations, they kind of focus more on the ground truth matching. So it's always like you're trying to evaluate using precision or recall, for which you kind of needed ground truth. And however, in recommended systems, it's super hard to find that ground truth because there's not a math problem that there exists a single gold standard of response. So it could be like whatever you like, another user may not like it, and so on. So this is a very difficult challenge, in my opinion. And there are also certain limitations of these LLM-based evaluations. So for example, there are like very little human representation. So these evaluators are kind of confined to the prompt templates and the existing data sets, and they can't really move on over these. And they are very, stuck with these certain prompt templates or whatever you have. So they often fail to capture the complexity and the dynamics of real users. So this is something. And obviously the LLMs were trained on unrestricted data over the internet. So they come with their own biases, and they also propagate these biases when we use them off the shelf. And as I have been mentioning over and over, ethical and privacy concerns. So the LLMs also have been dealing with, like, they are not often very sensitive or very good at handling with sensitive data, and this could raise potential ethical issues. So let's quickly move at the different trends that we have. So LLM or evaluation of GenerateSys has seen a very different, or a very I would say a different trend post 2023 and pre-2023, as you know, like that was 2023 was this year when like ChatGPT came into practice, and everyone was going crazy about LLMs. So pre-2023 evaluation was mostly static, and it kind of relied more on the ground truth-based metrics because there were not too much happening in the Gen AI space of conversations. And then key metrics were being used are the recall blue and so on. However, they were kind of failing to capture the interactive and the subjective nature of the dialogues and the conversation quality and so on. They were also not really like good for open-ended or free text responses. They were like good for like you want to search for something, you just get the item out of it. And they were also not assessing issues like hallucination and so on. However, post-2023, we saw that there was a huge rise of LLMs as judge, because now you can use them to evaluate the responses that were actually generated by another LLM. So there was a very big shift in the ideologies or the kind of way evaluation was being seen in research. Right, and now more important were like the practical problems like latency and like the mitigation of hallucination. These became like really important, more important than the traditional aspects. So this brings us to the quick summary. So then, as we saw, that evaluation kind of moved from a very static to a very multidimensional and very interactive paradigm. So we kind of had from a single gold standard, matching a gold standard response using like traditional metrics like recall, precision, and DCG, so on. Now we have like more, interactive and matching like also the whole conversational quality or the whole aspect of the full system, basically. Right, and how much human-like it is or how interactive it is and adaptive and so on. We now also use LLMs as not just recommendation generation, but also for evaluating recommendations, which is, I would say, a shift in the paradigm, a shift in the way we see things and we evaluate things. And this new way of seeing things actually not only makes our systems more scalable, but also gives rise to certain ethical considerations which we have discussed. And with this, I would like to conclude my section and invite Yasher to continue discussing the open challenges and the future directions of RecSys.
All right, so thank you. We are reaching the conclusion of this tutorial. Apologies, it has been a condensed, let's say, number of slides, which is reflection of our survey that is coming to appear online in the next few days. So you're all welcome to double check our survey for the pointers to actually references, and also the slides would be available. They're already available actually on the link provided. I'm going to show the QR code at the end, so you're welcome to use it. Actually, if you use that QR code, also the paper would be published there, like the archive version. Like before we go on, we are going to have a QA, but if there are like quick questions and interaction, you're welcome to post just to make it a little bit more interactive. But we will have a QA session for sure at the end. Are there like quick observation you want to have for from audience? Okay, we can come back to this toward the end of the tutorial. We discussed about essentially everything from definitions, from the goal of conversational recommender system, like different systems beside them, which could be, let's say, created in a modularized way, which would be created in a unified manner, thanks to deep learning and generative architecture, and agents, right, language agents. Then we discussed about essentially particularities of these systems and the replication. We discuss about knowledge and data foundation, like which kind of knowledge they use from different sources, knowledge graphs, and so on and so forth. We discuss about simulation, their goal, like different level of granularity of simulation, which could start from syntactic data to observational data to full simulation. And the core aspect of the evaluation, various questions, essentially various WH questions that we can formulate to conduct an evaluation of a conversational system. As evaluation of a recommender system, in particular conversational systems, are multifaceted. So one needs to go beyond a single question of recommendation quality. Now, I'm going to conclude this tutorial by adding a little bit of more insight of like some limitation and challenges. This is just a snapshot of a few, but then we can have a QA session about them. So one thing that we can say here overall is that essentially one question that we can talk about is about the naturalness of this data set. So essentially, one of the core challenges is about the data set. So we discussed about the evaluation and existing benchmark, and I'm just posing a few extra interesting questions to ask. So some of this question about data set revolve, because what is different from a conversational recommender system task compared to a normal recommendation one-shot is that we don't only need preference of the users about items, but also we need natural language conversation. Like where could we get this data? And we don't have like real human-to-human conversation, right, to train our models. So one way is that you have crowd-working sources like to do this, or even to synthesize this, or to find other ways of like linking and merging data set and sources to build such data sets. So obviously, when doing so, one thing that is here, the key is that how natural these data sets are. And for example, humans, like how humans would interact when making movie recommendation versus current more syntactic settings. As you saw in the redial example, the scenario that it was discussed there were more like the system provides some items where the user provides opinion about, and this is like how the dialogue starts. And so this is something that is currently, let's say, a core challenge. And naturalness and also the scale or the size of the data set. Obviously, the bigger the data set that we have, the more we can do, the stronger models we can train, right? So there have been some efforts to synthesize this, like using language models or other systems. But typically these data sets have low quality of different points. So here, for example, you can see an idea like how we can build, we can have a dataset construction pipeline where essentially the core is that if we can build better dataset by harvesting data from natural conversation. So we start, for example, from a data source. There we try to identify subsets that are interesting. And from there we try to, for example, extract posts relevant to recommendation, and essentially normalizing and mapping this to our database. So, there are possibilities of having a dataset construction pipeline using existing sources like Reddit and, for example, Amazon datasets. So this is a valuable effort. I think currently a big issue in the conversational research in the RecSys field. And this is also a nice picture that can summarize in some way like the evolution of these data sets in the CRS fields, starting from MovieLens, where probably most of you are familiar with. In MovieLens, typically what we have is the user like the preference of the user to add items, and essentially the item themselves are the core that we have access to, right? And if you compare that, for example, with redial, you can see that now we have a sentence like, I like 2001, A Space Odyssey, and this movie. And I watched this movie last night, and it was pretty good. So this is like you don't have only the movies themselves, but also a verbal preference of the user toward them. So redial can be seen one step ahead compared to movie lens, which has only the item themselves and preference of the user toward them, toward building this. And now if you compare that with Reddit movie, that is a dataset built by the Julia McCullough's group, here you can see that you have something like this. It says something that I can focus on, but nothing too harsh. It can be strange and bizarre, but dreamy visuals and movements and smooth, blah, blah, blah. It's how I felt watching these movies for some reasons. And what you can see here is that the verbal preference of the user now is more natural, more complex, and multifaceted, right? And this is what we really need to build this kind of systems. So both context, both size and naturalness are the core. The other challenges that here also we can see is that this work might be notable to see is that here you can see comparison of a large language model on conversational task on 3 different data sets. And what you can see on the very, very right, for example, you have this model, large language model GPT, and we have a lot of other models that are like, you can see them as classical, traditional models. And you can see that LLMs basically outperform many of the existing fine-tuned models. So this is quite interesting to know, and some of the reason might be that existing models like engage in shortcut learning by focusing on repeated items. So this is quite interesting to know. Obviously, working with LLMs as conversational recommender, the issue is that you may be able to have better, in some sense, personalization capability, depending on the task, but there are also risks such as hallucination. So LLMs do not have knowledge about your item inventory, right? So they may suggest items that do not exist in your catalog. So the issue of hallucination. So in this case, the hallucination existed, obviously, but it was low. So these are like challenges that could be there. Another thing that is quite notable in the research of LLM-based recommenders is the issue of bias. This is a quite interesting plot. Essentially, what you can see, this is now doing. This is a comparison of recall of recommendation across different countries, and you can see that essentially a geographical region affects the quality of recommendation quite a lot. So if you can see like the lower plots, you can see country by country the qualities are changing dramatically. And there is also a significant popularity bias issues when working with LLMs. Obviously, this is attributable to the unregulated internet data that has been used to train this. This may introduce a whole lot of bias issues, for example, cultural bias. Like imagine you have dominance of certain cultures of internet, like they're using, I don't know, talking about music, for example, there's American music, there is European music, and then using this model, you may be imposing like cultures and norms of one nature to another one. Okay, so these are like the new risks that we are like introducing working with LLMs, essentially due to the unregulated internet data that has been used to train them. And more, we can say that some observation over these, I think I already mentioned. Other things that here we can say, and this is also quite interesting, is that typically when we have conversation, the data set that are available, typically conversation consists of long context queries followed by relatively shallow conversation. Okay, so this is what we can say. Typically, this is like how human arguably perform, like converse, and this is something that we can try to construct with LLMs as well, like syntactically. So, for example, we can ask an LLM to construct a contextual query using product reviews, and then we can evaluate conversational recommenders based on their ability to find right items, right? So, syntactically speaking, there's a lot of room here to work on and to use LLM not as a core recommender here necessarily, but like to help on the data augmentation and data generation. Okay. And we can also, as I said, we can try to look at like linking resources together, like Reddit, which have a lot of natural language preferences, with Amazon links as endpoints to build this kind of conversational data where you have natural language preferences and items. So a lot could be said about data sets. This is one of the notable things that here we can talk about. There is a lot also on the system part that we haven't talked about. So one notable thing that we have realized in the literature, a lot of works are still using, let's say, pre-trained large language models, and essentially conversational component and recommendation component are joined together. We can term many of these work as being more not really a conversational models, but rather a contextual recommender. So system that understand the context of the user, the intent of the user, but arguably they are not as desirable as needed. So as I said, possible new direction is that we can have scenarios where the user interact with the system by editing, for example, a very complex query, and the system can understand and respond to that. There's a lot of things we can see also on the system side. For example, using RAG strategies, retrieval augmentation generation, collaborative retrieval, which essentially combine the power of retrieval models with large language model. For the retrieval model, they gain precision. From the large language model part, they provide new insights. And the core advantage is that by grounding the retrieval on existing models, we can reduce hallucination quite a lot. On the user studies, which is a common paradigm, there are limitations. Notably, we know that user studies typically are expensive and generally non-reproducible. So this is one of the common issues, like with conducting research related to user studies or online A/B testings, outside of the industrial setting, user studies generally don't involve real user, and this is obviously an issue. Typically, when we are doing user studies, users are informed the tasks they're going to do, and this per se introduces some kind of biases because the users knows that there is going to be, but the real essence of the user studies should be that this is like not known and behind the curtain, right? So this is something that mostly companies can do, like by dividing their users into groups and doing A/B testing. And this is currently one of the major like approaches to test new things. And overall, user studies can be suitable for general knowledge items and domain, but are not usable in cases where user requires specific knowledge or expertise. And in that case, you may want to have more, like, at least you need to have expert type of user studies. So we can also have this final slide about the open challenges. We can talk about challenges related to the output of recommendation. which should not focus on only on accurate recommendation in conversational setting, but also on producing novel and diverse recommendation. And one thing that here is quite interesting and notable is that arguably with LLMs, if you can control some of their risks issues and unpredictability issues, they have arguably the advantage of providing serendipities recommendation. So things that are like beyond your preference area. And they can try to bring this notion of awareness, arguably. So for example, in areas, let's say like fashion, where you have in your inventory a lot of catalogs, you may a lot of time you are putting things like into the visibility of the shopper, of the user. That is not that she's not looking at that point, but bringing that at the right points makes her or him to remember this in her future purchases, right? So this notion is known as awareness and is something that we can arguably say that generative models can be pretty good at if they can be tailored to. And essentially, we are also moving to an area where these systems are not simply, let's say, reactive. We can say that the former models were pretty much reactive, but now they're more proactive, like they can also control or initiate or start a conversation. Lots could be said about ethical issues, which we didn't touch, biases, fairnesses, and ethical consideration. I just mentioned some example. Evaluation over time. This is something pretty important especially for industries where they want to see over a period of time, what is the amount of engagement I get and what are the overall aggregated, let's say, benefits or risks of using this system. And this is something that I think the community, not only in conversational research, but generally in recommender system, should focus on when evaluating this. This obviously needs evaluation at different standpoints in time, right? And especially for industries, scalability is an issue. For example, when you talk about agents, one needs to know the necessity of using agents in particular research and essentially the latency. Maybe latency when you're using with a classical retrieval model, latency is not even a factor you put in your paper, right? But working with agents is something that is notable to be used. Simply asking the question of, is my system notable? It really needs using a complex agentic system. And imagine the user using a conversational system, like having a basic query, and then you keep her or him waiting for 2 minutes to give a very simple response, right? Is that ideal? Would the user be willing to accept this? And this is quite important, like the timing and latency. Because you can see that, for example, if you are providing bad recommendation to the user, right? Imagine you have a system, like this is system A, system B. One of them is providing bad recommendation. Both of them recommending bad recommendation, but one keeps the user waiting like 5 minutes. So obviously the user would be much more pissed off if he or she has to wait 5 minutes, but still get bad recommendations. So she might be okay with a bad recommendation if you just are quick, right? So this is an important issue in conversational models because users are spending their times there. And integration of a lot of data, including multimodal data, as you have seen, for example, in the case of large language model, how much they're helping this area. So summary, conversational recommender system represent a promising area in RecSys research. And we need to go into building benchmark at dataset that are more human-like. And this line of research have somewhat blown up by excellent performance of large language models. There is still plenty to do here, and we have touched a little bit on those. And many traditional questions about recommender system evaluation fairness still hold, but now they need to reiterate it in the light of conversational paradigms. So with that, I would like to conclude our tutorial and thank everyone for their attention. If there are questions, please feel free to ask. So we would love to hear them. Thank you much.
Do we have enough work done on RLPF in conversation CRS?
Well, I think alignment in general is a core issue. I'm not super updated on that, to be honest, but I think generally speaking, RecSys research is a little bit behind the ML community on this. But what your point reminds me about this question is that if you look at the pipeline of tuning an LLM, we have this core base tuning of the model where the models are trained to follow instructions. And then you have the follow-up of alignments. And one notable thing that here I think we can work on is essentially working on this final alignment step to be more societal as a mitigation strategy for the biases that we have. So the method you mentioned is a notable one, but if this alignment could be done more at the society level is an interesting. So a simple research question here would be given this large language model used for my conversational research, how can I make more ethically aligned to human norms and values, right? And the tuning step could be done on that research area. My general observation, according to the surveys we have written, is that on this, RecSys is quite behind the ML community, but I can double check that for you.
So I mean, like how to say balance the cost of LLM inference with the quality of the conversations, because I think it's a big barrier for adaptation in many industry applications.
Right, there's a lot of costs. I think if I hear about costs, you mean the money specifically,
the
API costs,
running the GPUs and so on.
Yes, or the GPU training, right? So I think this is an absolutely important thing that I think we should put in the evaluation of also the models. We should, when reviewing papers, at least what we can do is to ask users to put up the cost for this service, because this is something that is typically behind the curtain. We don't know that we are showing, okay, this recall one better than the others, but how much API calls you have had, simply speaking, how much CO2 emission you have caused, how much water things you have caused, no? And these are typically, to be honest, we are ignorant on, arguably because we are a bit hedonistic toward recommendation quality, and this is what we can bias the reviewer on. I think working with LLM, this is absolutely important, and this is a very good observation. With agents, it's become even more important to show there. And I think a very simple thing is that you can log in your code at least the amount of timing, the API calls you have, the CO2 emission. There are libraries that you can capture, and we can try to move into the direction of benchmarking these aspects into RecSys. Actually, it's RecSys in the benchmarking, dataset benchmarking thing. Now I see there are papers coming on this more sustainable aspect of recommendation evaluation. So I think this is a very, very good question and very right time to work on.